Settle into the sleepy mind channel, and tonight we will explore the Cambrian period. Around 541 million years ago, the shallow oceans of the world entered a phase of change that would quietly reshape life in the sea. Over a comparatively short span of geological time, bodies that had once blended into fine-grained mud began to take on clearer outlines. New ways of moving appeared across the seafloor, and the physical relationship between water, ground, and living form started to deepen. The Cambrian period marks the point at which the ocean floor became an active landscape of interaction, rather than a largely passive surface of settling mud. Across broad continental shelves, fine sediment continued to drift down through sunlit water, forming soft layers that were reshaped by low-energy flow. Within this setting, the character of life began to change in ways that left more durable traces in the sedimentary record. These physical conditions helped shape the early diversification of marine life in the Cambrian seas. The chemistry of these shallow waters was changing slowly. Oxygen mixed into surface layers more thoroughly than in deeper zones, carried by waves and slow currents that stirred the upper ocean. This allowed living tissues to sustain more continuous internal activity, even as outward forms remained understated. Minerals circulated through the water, dissolving from distant rock and settling again as fine particles, quietly altering the balance of materials available to living systems. These changes unfolded over long spans of time, building conditions that did not yet transform the visible face of life, but that expanded what life could support within itself. Across the wide expanse of these early seas, the seafloor functioned as a broad working surface for subtle biological change. Layers of sediment accumulated and were compressed, then overlaid by new deposits, recording the slow motion of the environment while erasing many of the delicate traces of the organisms that once lay upon them. In this setting, the groundwork was being laid for shifts in form and behavior that would later become visible in stone, even though the surface of the world still appeared calm and sparsely structured. Around 541 million years ago, the world entered the span of time now called the Cambrian period, a boundary marked in stone by changes in the kinds of traces life left behind. In the early Cambrian seas, broad continental shelves lay beneath warm, shallow water, their surfaces coated in soft seafloor mud that shifted gently under the movement of currents. The water carried fine particles in slow suspension, and when these grains settled, they formed smooth layers that could be reshaped by the faintest disturbance. This was the setting in which earlier forms of life had lived for long ages, pressed lightly into surfaces that yielded and recovered with each passing flow. Before the Cambrian began, most visible life in the oceans had been simple in structure. Bodies lacked rigid frameworks and rested directly against the seafloor, supported by soft tissues that bent and relaxed with the movement of water. Many of these earlier organisms lay across microbial films that bound fine sediment into thin, cohesive sheets. These living carpets stabilized the seabed while also providing a source of nourishment for organisms in contact with them. Movement across such surfaces was subtle and slow, more like a gradual shift in position than a purposeful stride, and the softness of both body and ground meant that impressions were easily smoothed away. As the Cambrian approached, environmental conditions in these shallow seas were already changing. Oxygen mixed more thoroughly into surface waters, as waves and currents stirred the upper ocean, allowing living tissues to draw on a steadier supply of energy. The chemistry of seawater shifted as minerals dissolved from distant rock and were carried across continental shelves, subtly altering the materials available to developing organisms. These changes did not yet produce shells or hard outer coverings, but they allowed internal biological processes to sustain more defined arrangements of tissue. Bodies could hold their shape for longer against the constant pressure of surrounding water, maintaining posture instead of collapsing into the surface beneath them. The transition into the Cambrian is marked in the fossil record by a sudden clarity of form. Earlier soft-bodied communities left only faint outlines in stone, while early Cambrian layers preserve more distinct traces of living shapes. This contrast reflects the physical reality of preservation. Soft tissues decay quickly and collapse under their own weight, while even slightly firmer structures press deeper into sediment, leaving impressions that are more likely to be captured as layers build above them. The difference between these records is like the difference between a footprint left in loose powder and one pressed into damp clay. Both are made by contact, but only one holds its shape long enough to be sealed beneath new layers of material. Many of the earlier soft-bodied forms that dominated Precambrian seas disappear from the fossil record as the Cambrian begins. Their absence does not signal a single moment of extinction, but a gradual replacement as new forms became better suited to the changing physical and chemical conditions of the seafloor. As bodies began to interact with sediment in more assertive ways, the microhabitats shaped by microbial films and soft surfaces were altered. Subtle ridges and depressions formed where organisms pressed against the ground, changing how water moved across the surface and how fine particles settled. These small physical changes accumulated across the seafloor, reshaping the environment in which later Cambrian life would develop. The early Cambrian seas remained entirely marine, with life confined to the shallow waters that spread across continental margins. Land beyond the shoreline was largely barren, offering no rooted plants to stabilize sediment or moderate runoff. Fine particles eroded from exposed rock were carried directly into coastal waters, spreading into thin veils across the shelves. Over time, these deposits compressed into stone, recording the slow motion of sediment and the growing clarity of biological traces. The physical continuity of this environment masked the biological shift underway, as the same warm, shallow seas now supported bodies that interacted with the seabed in more varied ways. Within these early Cambrian communities, bodies began to adopt postures that changed how they experience flow. Some forms lifted parts of themselves slightly into moving water, increasing exposure to currents that carried suspended nutrients. Others maintained broader contact with the sediment, spreading their weight across soft surfaces to remain stable as water passed over them. These differences in how bodies met the physical forces of their surroundings influenced which forms could persist in particular patches of the seafloor. The environment did not suddenly transform, but the range of biological responses to it widened, allowing more varied arrangements of tissue and posture to remain viable. The boundary into the Cambrian thus marks a change in how life occupied space in the ocean. Earlier communities were shaped by softness, flexibility, and environments that erased fine detail. The early Cambrian began to support bodies that could maintain shape against subtle forces, pressing more durable impressions into sediment. This shift altered how life was recorded in stone, giving the impression of a sudden flowering of form. In physical terms, it reflects a gradual strengthening of the dialogue between living bodies and the seafloor they inhabited, as organisms began to leave clearer marks upon the surfaces that supported them. The sunlit Cambrian shelves continued to move through long cycles of deposition and compression. Fine layers of sediment settled, were overlaid by new deposits, and slowly hardened into rock. Within these layers, the traces of early Cambrian life accumulated, preserving the outlines of bodies that had begun to assert their presence more firmly against the yielding surface of the seabed. The world itself remained quiet in motion, but within its waters, the groundwork for a more visibly complex marine community was being laid. In the late Ediacaran seas, just before the Cambrian, many organisms lived as broad, flattened bodies on microbial surfaces, and the preservation of their impressions depended on rapid burial in very fine sediment. Where sediment arrived slowly, outlines were erased, and where it arrived quickly, the surface could capture a brief silhouette before the tissues softened and disappeared. This uneven preservation means that the approach to the Cambrian boundary is recorded as a patchwork, with some places preserving clearer impressions and others preserving almost none. As the Cambrian began, the kinds of traces preserved widened, and the boundary became more visible in stone, not because the ocean suddenly changed its basic character, but because the dialogue between bodies and sediment began to leave stronger physical signatures. In the early Cambrian seas, the variety of living forms began to widen in ways that were visible in the traces left behind on the seafloor. Shallow continental shelves, still warmed by sunlight and stirred by slow currents, now carried a growing range of body outlines pressed into yielding sediment. Where earlier layers of rock recorded only faint impressions, early Cambrian layers began to preserve clearer shapes, reflecting a change in how bodies interacted with the ground beneath them. The same gentle movements of water continued to smooth the surface of the seabed, yet the marks left by living forms became more distinct, lingering long enough to be sealed beneath settling layers of fine material. This increase in visible diversity unfolded over a relatively short span of geological time within the Cambrian period. The rock record shows a rapid rise in the number of recognizable body designs, creating the impression of a sudden expansion of complex life. In physical terms, this reflects a convergence of biological change and environmental context. As bodies developed more defined forms, their contact with sediment produced deeper impressions. At the same time, the steady accumulation of fine particles across the Cambrian shelves created conditions where those impressions were more likely to be preserved. The difference between earlier and early Cambrian records lies not only in the number of forms present, but in how readily their presence could be captured by the sedimentary process. Across the Cambrian seafloor, this widening of form played out unevenly. In areas where currents were stronger, bodies that could maintain their shape against flow left clearer traces, as the pressure of moving water pressed them more firmly into the substrate. Where sediment was finer and more easily reworked, forms that spread their contact across a broader surface found stability, leaving impressions that resisted being smoothed away by passing currents. These local differences created a patchwork of preserved traces, with some surfaces densely marked by overlapping impressions and others showing only scattered signs of contact. The rapid diversification of body arrangements during the Cambrian reflects an interval of evolutionary experimentation in which many different ways of organizing tissues appeared. Some of these arrangements proved short-lived, vanishing from the record as conditions shifted or as other forms occupied similar spaces more effectively. Others persisted and became the foundations of lineages that would continue into later periods. The Cambrian seafloor thus recorded not only an increase in variety, but also a process of continual adjustment, as new designs were tested against the physical constraints of water, sediment, and flow. The causes of this early Cambrian expansion are still examined through multiple lines of evidence. Rising oxygen levels in surface waters supported more sustained activity within living tissues, allowing bodies to maintain posture and movement over longer intervals. Genetic systems that governed how tissues were patterned permitted new spatial arrangements of parts, expanding the range of viable forms. The physical setting of the Cambrian shelves, with their shallow depths and broad expanses of sediment, provided a continuous surface upon which these new designs could interact with the environment and with one another. Together, these factors created a setting in which the variety of visible forms increased rapidly. The apparent suddenness of this change puzzled early interpreters of the fossil record, because the layers below the Cambrian boundary preserved so little of the soft-bodied world that preceded it. As additional early Cambrian sites were discovered and studied, it became clear that the record itself had changed in clarity. The physical processes of preservation began to capture details of bodies that earlier sediments had erased. The seafloor became a surface on which the interactions of living forms left more enduring marks, allowing a richer picture of Cambrian life to emerge from stone. Within these early Cambrian communities, interactions among organisms grew more complex as the number of distinct body forms increased. Overlapping impressions on the seafloor show that multiple forms occupied the same spaces, pressing into the same soft surfaces at different times. Tracks crossed resting marks, and shallow depressions overlapped one another, recording a denser pattern of activity than in earlier layers. The Cambrian seabed thus became a more crowded physical surface, shaped by the cumulative contact of many bodies moving, settling, and shifting position across the same ground. The physical continuity of the Cambrian environment remained. Shallow, warm seas continued to spread across continental margins, and fine sediment continued to drift down through the water column. What changed was the character of the biological dialogue with this environment. Bodies that could maintain defined outlines against the gentle forces of water and sediment left clearer records of their presence. The rapid expansion of visible diversity during the Cambrian reflects this shift in how life occupied space in the ocean, producing a seafloor marked by a growing variety of enduring traces that would become embedded within the layers of rock that followed. In the earliest part of the Cambrian, the rock record begins to capture a succession of small, durable traces that bridge the earlier world of faint impressions and the later world of clearly preserved animals. Tiny mineralized pieces, often grouped as small shelly fossils, appear in many early Cambrian deposits. They can be fragments of protective coverings, spines, or the hard parts of organisms that were otherwise soft, and their presence suggests that the Cambrian expansion was not a single step, but a layered shift in how bodies were built and recorded. In the same interval, trace fossils become more varied, with burrows and trails indicating that movement across and within sediment was becoming more common. Each shallow track is a physical signature of an animal interacting with the Cambrian seabed, pressing into the mud, lifting away and pressing again, leaving a sequence of contact points that could be buried and preserved. Within these Cambrian shelves, diversification also reflects the widening of ecological roles. Some animals exploited microbial films directly, grazing across the surface, while others filtered or collected particles from moving water. A body plan that lifts a feeding surface into gentle flow experiences a different delivery of suspended material than one that remains flush against the sediment. The Cambrian environment rewarded these differences because currents varied across short distances, and small changes in posture could shift an animal into a richer stream of nutrients. The increase in visible diversity therefore includes the emergence of new ways to occupy space, from low profiles on the substrate to forms that projected into the water column and encountered a more dynamic physical regime. In the early Cambrian period, most life remained confined to the oceans, and the surface of the planet was defined by water rather than land. Broad continental shelves lay beneath shallow sunlit seas, while the land beyond the shoreline remained largely barren and rocky. There were no rooted plants to anchor soil, and no animals yet moving across exposed ground. Wind and rain carried fine particles from exposed rock faces directly into the Cambrian seas, where they spread across the shelves as thin veils of sediment. These inputs continually refreshed the soft surfaces of the seabed, shaping the environments in which Cambrian life developed. The shallow Cambrian oceans were generally warm, allowing surface waters to circulate gently across wide expanses. Sunlight penetrated into these upper layers, supporting the growth of microbial communities that coated sediment with thin, living films. These films bound fine grains together, stabilizing the surface while still allowing it to be reshaped by passing currents. In some areas, the seafloor lay in broad, gently sloping plains, while in others, it rose into low ridges formed by uneven sediment deposition. These subtle variations in the physical landscape created differences in how water moved across the bottom, altering where fine particles settled and where they were more easily lifted and redistributed. Across the Cambrian shelves, currents traced slow paths driven by differences in temperature and the movement of tides. Where water flowed steadily, sediment was kept in motion, smoothing the seafloor and maintaining soft, pliable surfaces. Where currents slowed, fine particles accumulated, building thicker layers of mud that compressed under their own weight. Living forms that rested against these surfaces experienced different physical conditions depending on where they settled. In areas of gentle flow, bodies could maintain contact with the sediment without being disturbed, while in more active zones, subtle shifts in posture were required to remain stable against the moving water. The Cambrian climate contributed to the character of these shallow seas. During much of the period, there were no extensive polar ice caps to draw down sea levels. As a result, high sea levels covered large areas of the continents, extending shallow marine environments far inland from the margins of exposed land. The physical breadth of these shallow seas meant that similar environments appeared across distant regions of the planet. Cambrian marine habitats formed a network of warm, sunlit shelves, connected by broad stretches of ocean that allowed similar physical conditions to occur on widely separated continental margins. The arrangement of continents during the Cambrian differed from that of later periods. Much of the planet's landmass lay in the southern hemisphere, and coastlines traced unfamiliar outlines compared to those of the present day. Despite these differences in geography, the physical processes shaping the Cambrian seas were consistent. Waves mixed oxygen into surface waters, currents redistributed sediment and nutrients, and fine particles settled to form the soft beds upon which early Cambrian life rested. The repetition of these processes across multiple regions created comparable settings for the emergence and persistence of early marine communities. Within these widespread shallow seas, Cambrian life experienced a continuous interplay between water movement and sediment stability. Bodies resting on the seabed were shaped by the pressure of overlying water and the subtle drag of passing currents. A form that lay flush against the sediment encountered less force from moving water, while one that lifted even slightly into the flow experienced greater pressure. This difference in exposure influenced where particular forms could persist. Areas of calmer water favored bodies that spread across the surface, while regions with stronger currents selected for postures that reduced drag or allowed movement with the flow. The absence of vegetation on land meant that sediment supply to the Cambrian oceans was unbuffered. Rainfall and surface runoff carried particles directly from exposed rock into coastal waters, where they dispersed across the shelves. This steady input maintained the softness of the seafloor, ensuring that the substrate remained responsive to contact and movement. Each new layer of sediment compressed those beneath it, gradually hardening the lower layers into stone while leaving the upper surface pliable. The continual renewal of this soft surface shaped how Cambrian organisms interacted with their environment, as the ground beneath them was always in the process of becoming something more permanent. The early Cambrian oceans thus formed a continuous physical stage for biological activity. Warm, shallow waters extended across large areas of the planet, offering broad, gently contoured surfaces upon which life could spread. The physical properties of these environments, shaped by climate, geography, and sediment supply, created conditions that supported the diversification of Cambrian forms. Within this setting, bodies pressed into soft ground, lifted into flowing water, and left impressions that recorded the dialogue between life and the shallow seas that define the Cambrian world. The Cambrian geography also shaped the character of these seas by determining where shallow platforms formed and where sediment was delivered. Some continental blocks sat nearer the equator and experienced strong evaporation and warmth, encouraging the formation of carbonate-rich waters on broad shelves. In such settings, fine carbonate mud could settle out of the water column and form soft, pale layers across the seabed. Elsewhere, shelves received more clay and silt from exposed rock, creating darker, more easily compacted muds. Storms and seasonal shifts in wind could drive pulses of wave energy across the Cambrian shelves, briefly increasing mixin and pushing oxygenated water deeper, then easing again into calmer circulation. The seafloor experienced these pulses as alternating periods of gentle stability and brief reworking, with thin veneers of new sediment spread across earlier surfaces. Tides in nearshore Cambrian waters could also be pronounced across wide, gently sloped platforms. The back and forth movement of water across these flats changed the direction of near-bottom currents, reshaping how fine particles were deposited and how microbes colonized the sediment surface. A resting body would experience flow that first approached from one side, then from another, and the near-bottom boundary zone of water around that body would be continually refreshed and reformed. This shifting physical context created opportunities for different postures and feeding strategies, reinforcing the variety of niches available in the Cambrian coastal seas. Across these Cambrian shelves, the daily cycle of light also mattered. Morning light strengthened surface warming and mixing, while evening calm allowed fine particles to settle, laying down thin films that could quietly seal fresh traces. In the early Cambrian seas, the character of life was shaped not only by the forms of bodies present, but by the chemistry of the water that surrounded them. Oxygen mixed into the surface layers of these shallow oceans through the action of wind, waves, and slow-moving currents. As water moved across broad continental shelves, it carried dissolved gases down into contact with the seafloor, refreshing the thin layer of oxygen available to organisms resting against the sediment. This steady renewal altered how long tissues could sustain activity without becoming starved of the energy required for movement, growth, and repair. Earlier marine environments had supported life under more limited oxygen conditions, where internal processes had to proceed at a slower pace. In the early Cambrian, increased oxygen availability in surface waters allowed tissues to maintain continuous activity over longer periods. Cells could sustain the chemical reactions that supported movement and structural tension, enabling bodies to hold posture instead of collapsing into the substrate beneath them. The difference in physical terms can be felt in how a structure behaves when air flows freely through it compared to when that flow is restricted. With greater access to oxygen, tissues were less constrained by internal limits, allowing more persistent interaction with the surrounding environment. The mixing of oxygen into Cambrian seas was not uniform. In the shallowest waters, sunlight warmed the surface and encouraged circulation, allowing oxygen to be replenished regularly. In slightly deeper or more sheltered areas, renewal was slower, and pockets of lower oxygen could develop near the sediment. This created gradients across the seafloor, with some patches offering more sustained support for active tissues than others. Organisms settling in these different zones experienced subtle but important differences in how long they could remain active while resting against the sediment or lifting parts of their bodies into moving water. As oxygen levels in surface waters rose relative to earlier periods, the balance of what kinds of bodies could persist shifted. Tissues capable of maintaining shape against slow-moving currents were more likely to remain functional in oxygen-rich zones, while in lower oxygen patches, only forms adapted to slower internal rhythms could persist. This uneven distribution created a mosaic of microhabitats across the Cambrian shelves, each favoring slightly different arrangements of tissue and posture. Over time, these physical differences contributed to the variety of forms preserved in Cambrian layers of rock. The influence of oxygen extended beyond simple survival. With greater access to this dissolved gas, organisms could sustain more complex internal coordination. Tissues responsible for movement could contract and relax with greater regularity, allowing bodies to reposition themselves more frequently across the seafloor. This did not yet produce rapid locomotion, but it did allow for more continuous adjustment of posture. A form resting against the sediment could lift part of its body into flowing water, then settle again, maintaining contact while also sampling different layers of the surrounding environment. These small shifts altered how organisms encountered suspended nutrients and how they experienced the drag of currents. The chemistry of Cambrian seawater also influenced the availability of dissolved minerals. As currents moved across continental shelves, they carried ions released from weathered rock into coastal waters. These materials circulated through the shallow seas, creating a background chemical environment in which living tissues developed. While the widespread formation of hard shells would become more prominent in later chapters, even at this stage, the presence of dissolved minerals shaped the internal processes of early Cambrian organisms. The physical environment provided not only oxygen, but a circulating supply of materials that supported the maintenance of tissues and the gradual strengthening of biological structures. Across the Cambrian seafloor, the interplay between oxygen renewal and sediment movement created dynamic conditions. Fine particles settled from the water column, forming soft layers that were periodically disturbed by passing currents. As these layers accumulated, they compressed those beneath, slowly reducing the porosity of deeper sediment. Near the surface, however, water could still circulate between grains, allowing oxygenated water to penetrate into the uppermost layers of the seabed. Organisms resting on or within these layers experienced a continuous exchange between their bodies and the surrounding water, shaped by how freely oxygen could move through the spaces between sediment particles. This exchange influenced how long organisms could remain in contact with the sediment without repositioning. In areas where water moved easily through the upper layers of the seabed, oxygenated water refreshed the immediate environment of resting bodies, allowing tissues to remain active for longer periods. In zones where sediment was more compacted and circulation was reduced, organisms were more constrained, needing to shift position or lift portions of their bodies into better oxygenated water to maintain internal processes. These subtle physical constraints shaped patterns of movement across the Cambrian sea floor, encouraging repeated, gentle adjustments rather than prolonged stillness. The early Cambrian oceans thus presented a complex chemical landscape layered over a physically soft substrate. Oxygen availability varied across space and time, renewed by surface mixing and limited by local conditions near the sediment. Organisms interacted with this landscape through their posture and contact with the seafloor, adjusting how much of their surface area was exposed to moving water. The ability to maintain defined forms against mild, near-bottom flow was supported by this chemical context, as tissues with access to sufficient oxygen could sustain tension and shape more effectively. Within this setting, the dialogue between living bodies and their environment became more active. The Cambrian shelf waters offered not only physical space, but a chemically supportive medium that allowed tissues to persist in more defined arrangements. This combination of oxygen renewal, sediment interaction, and internal biological capacity contributed to the broader pattern of diversification unfolding across the Cambrian shelves. Bodies pressed into soft ground, lifted into flowing water, and settled again, continually adjusting to the subtle gradients of chemistry and movement that characterize the early Cambrian world. In parts of the Cambrian seafloor, oxygen could form temporary oases where mixing was stronger, then thin again when water became still and sediment pores filled. This shifting boundary between oxygenated and less oxygenated conditions influenced how long animals could remain settled in one place before adjusting posture or moving toward fresher flow. In the early Cambrian seas, a quiet but consequential change began to appear in the way some bodies met the surrounding water and sediment. Along portions of the seafloor, the outlines of certain organisms pressed into soft mud with firmer edges than before. Where earlier forms left only gentle impressions that blurred as currents passed over them, some early Cambrian bodies now held their shape with greater resistance. This change was not uniform across all forms, but it altered how living tissues interacted with the physical environment, allowing certain surfaces to maintain sharper boundaries against the yielding substrate beneath them. The presence of firmer outer layers changed how bodies distributed pressure across the seafloor. When a soft form rested against mud, its weight spread evenly, and the contact area conformed closely to the contours of the surface. As firmer coverings began to appear, contact with the sediment became more localized. Pressure concentrated along defined edges and points of contact, pressing deeper impressions into the substrate. The seafloor responded differently to these contacts, forming grooves and depressions that resisted being smoothed away by low energy flow. These changes in how bodies pressed into sediment altered the texture of the Cambrian seabed, adding a new layer of physical complexity to the surface across which organisms moved and rested. The development of firmer outer structures also influenced how bodies encountered moving water. Soft tissues deform easily under flow, allowing water to pass around them with little resistance. When portions of the body became more rigid, the flow of water around those surfaces changed. Currents parted more sharply at defined edges, creating small zones of altered pressure along the body surface. This changed how suspended particles moved around the organism, affecting the delivery of nutrients and the removal of waste from the immediate boundary between tissue and water. The physical relationship between body and current became more structured, shaping the microenvironment that surrounded each form. These early firmer coverings were composed of materials drawn from the surrounding seawater. The shallow Cambrian oceans carried dissolved minerals released from weathered rock on nearby land masses and redistributed by currents across continental shelves. As organisms incorporated these materials into their tissues, they produced surfaces that were more resistant to deformation. Some early Cambrian forms began to use calcium carbonate, while others employed different mineral compositions. The availability of these materials varied across regions of the Cambrian seas, influencing where firmer coverings could develop and persist. In areas where dissolved minerals were more abundant, the emergence of mineralized surfaces was more pronounced, while in other regions, soft-bodied forms continued to dominate. The appearance of firmer outer layers altered how organisms interacted with the fine-grained mud beneath them. Bodies resting on the seabed no longer merged as seamlessly with the surface. Instead, defined edges created slight gaps where water could circulate between body and substrate. This circulation refreshed the immediate environment beneath resting forms, bringing oxygenated water into contact with tissues that were pressed close to the ground. The difference between a surface pressed flush against mud and one lifted slightly by firmer edges shaped how long tissues could remain in contact with sediment without becoming deprived of oxygen. This small physical change influenced where organisms could settle and how long they could maintain a given posture. As firmer coverings became more common in parts of the Cambrian seas, the preservation of biological traces changed accordingly. Bodies with more resistant surfaces were more likely to leave durable impressions when pressed into sediment. When such an organism moved across the seabed, the edges of its body could carve shallow grooves that persisted long enough to be sealed beneath settling layers of fine material. Over time, these impressions accumulated in the rock record, contributing to the richer fossil record characteristic of the Cambrian period. The increased clarity of preserved traces reflects not only the presence of firmer structures, but the altered physical dialogue between bodies and the substrate they contacted. The emergence of firmer outer layers also shaped interactions among organisms. As bodies became more resistant to deformation, contact between forms produced different physical outcomes. When two soft bodies met, their surfaces deformed and yielded, distributing pressure evenly. When firmer surfaces met, contact produced more defined points of pressure, altering how bodies adjusted position relative to one another. This influenced how multiple forms shared space on the Cambrian seabed, contributing to changes in spacing, posture, and patterns of overlap. The presence of firmer coverings altered the texture of interactions across crowded surfaces. Within the broader context of the Cambrian seas, the appearance of firmer outer layers did not replace soft-bodied forms entirely. Many organisms continued to rely on flexible tissues, and large expanses of the seabed remained dominated by soft-bodied life. The early Cambrian environment supported a mixture of forms, with varying degrees of resistance to deformation. This mixture created a layered physical landscape, in which bodies of different firmness interacted with sediment and currents in distinct ways. The seabed thus became a surface marked by a range of impressions, from gentle smudges left by soft tissues to sharper grooves formed by firmer edges. The consequences of these changes extended beyond individual bodies. As firmer surfaces altered patterns of contact with sediment, they influenced how fine particles settled and were redistributed across the seabed. Grooves and depressions formed by firmer bodies created microchannels that guided the movement of water along the surface, subtly reshaping local flow patterns. These microcurrents affected where fine sediment accumulated and where it was more likely to be lifted and carried away. Over time, the cumulative effect of many such interactions contributed to the evolving texture of the Cambrian seabed, reinforcing the interplay between biological form and physical environment. In the early Cambrian oceans, the gradual appearance of firmer outer layers thus marked a shift in how life engaged with water and sediment. Bodies that could maintain defined edges altered the flow of currents around them, pressed more durable impressions into the seabed, and changed the immediate chemical and physical conditions at the boundary between tissue and environment. These changes did not yet dominate all aspects of Cambrian life, but they added a new dimension to the physical relationships shaping early marine communities. the seabed continued to renew itself under layers of settling sediment, yet within each new layer, the traces of firmer forms became part of the record that would endure as the Cambrian seas moved through their long cycles of change. In the early Cambrian seas, the appearance of bodies built from repeated segments introduced a new kind of structure into the marine environment. Along the soft seabed mud of the Cambrian seabed, some organisms carried their weight across a series of linked sections, each one aligned with the next, to form a continuous but articulated surface. When these bodies pressed into mud, the contact was distributed across multiple firmed regions rather than across a single continuous soft surface. The result was a pattern of impressions that reflected the underlying segmentation, leaving faint ridges and grooves in the sediment that mirrored the repeated divisions of the body above. Trilobites became among the most common of these segmented forms in the Cambrian oceans. Their bodies were arranged into distinct regions, with repeated segments allowing flexibility while maintaining structural coherence. As trilobites moved across the seabed, the articulation between segments allowed the body to follow subtle contours in the sediment without losing overall shape. This capacity to conform to uneven surfaces while remaining mechanically integrated altered how these animals experienced contact with the ground. The seabed, rather than presenting a uniform plane, became a textured landscape to which segmented bodies could adapt with each shift in posture. The segmented construction of trilobites changed how pressure was transmitted through the body to the substrate beneath. Each segment bore a portion of the animal's weight, spreading contact across a series of defined points. When a trilobite settled, its exoskeleton pressed into soft mud in a pattern that reflected the repeated ridges of its body. As currents passed over, fine particles settled into the shallow depressions between these ridges, briefly outlining the segmented form before being smoothed away by later movement. The seabed thus carried a temporary map of the trilobite structure, recording how the animal's body was organized in space. Movement across the Cambrian seabed placed additional demands on segmented bodies. As trilobites crawled, the articulation between segments allowed the front of the body to rise slightly over small ridges of sediment, while the rear followed, adjusting to the same contour moments later. This staggered contact with the surface reduced the tendency for the body to catch on uneven patches of mud, smoothing the passage across the seabed. The mechanical relationship between segment and substrate allowed these animals to navigate a surface that was never perfectly even, shaped by constant deposition and redistribution of fine sediment. Trilobites also possess the ability to curl their segmented bodies into a compact form. When threatened or disturbed, the articulation between segments allowed the body to fold inward, bringing firmer outer surfaces together. This change in posture altered how the animal interacted with the surrounding water and sediment. In a curled position, contact with the seabed was concentrated along a smaller area, pressing more deeply into the mud. The surrounding water flowed around the compact form in a different pattern, reducing exposure of softer surfaces to direct currents. This physical reconfiguration changed the immediate microenvironment around the animal, influencing how particles settled and how oxygenated water circulated near its body. The presence of segmented forms like trilobites altered the texture of the Cambrian seabed. As these animals moved, rested, and curled, they created a series of repeated impressions and disturbances in the sediment. Each movement pressed and lifted different segments against the ground, creating shallow furrows that were partially filled by settling particles before being reshaped by subsequent currents. Over time, the cumulative effect of many such interactions produced a seabed marked by patterns of segmented contact, reflecting the growing abundance of trilobites in early Cambrian communities. The environment of the Cambrian seas shaped how segmented bodies could persist. In areas of stronger current, the ability of trilobites to conform to the seabed reduced drag and helped maintain stability against moving water. In calmer zones, segmented articulation allowed these animals to settle into the yielding sediment without becoming trapped as layers compacted beneath them. The flexibility of their construction provided a balance between rigidity and adaptability, enabling sustained contact with the shifting surface of the seabed. This balance influenced where trilobites could occupy space within the mosaic of Cambrian habitats. The widespread presence of trilobites in Cambrian deposits reflects how well their segmented body plan suited the physical conditions of shallow marine shelves. Their articulated exoskeletons interacted with sediment and currents in ways that left durable traces in the fossil record. When trilobite remains were buried by successive layers of sediment, the firmness of their outer surfaces preserved the segmentation of their bodies in stone. This clarity of preservation contributed to the prominence of trilobites in Cambrian fossils, shaping modern understanding of early marine life. Across the Cambrian seas, segmented bodies introduced a new mechanical relationship between life and environment. The repetition of structural units along the body allowed movement and stability to coexist, enabling organisms to adapt to the uneven, constantly shifting seabed. Each segment contributed to the overall contact with sediment, distributing pressure and allowing posture to change without loss of coherence. The early Cambrian seabed thus became a surface shaped not only by soft contact, but by the repeated, articulated touch of segmented forms moving across it, leaving patterns that would endure within the layers of rock that followed. The trilobite body plan also allowed growth through repeated molting, a process that left behind shed exoskeletons within Cambrian sediments. As a trilobite outgrew its rigid outer covering, it had to split and emerge, briefly exposing softer tissues before the new exoskeleton hardened. This moment of vulnerability tied the animal's life history to the physical safety of the seabed, favoring places where a trilobite could settle into sediment or shelter behind small ridges and depressions while it completed the transition. The discarded exoskeleton, still segmented and durable, could be buried by settling mud and preserved, adding to the abundance of trilobite remains in Cambrian deposits. Many trilobites also possessed calcite-rich compound eyes, structures that interacted directly with the light of shallow Cambrian waters. Light filtering down through clear seas would strike the facets of these eyes, and the physical placement of the eyes influenced how a trilobite oriented itself on the substrate. A body that can detect contrast and motion across the seabed is more capable of maintaining safe spacing, avoiding obstacles, and responding to approaching movement in the water above. Even in a calm setting, vision changes posture. It encourages subtle adjustments, a slight lift of the head region, a shift in angle relative to the current, and these small changes alter the patterns of contact between body and sediment. In the early Cambrian seas, the growing variety of body forms included organisms capable of actively pursuing others through open water or along the seabed. The presence of such predators altered the physical dynamics of Cambrian marine environments, introducing new patterns of movement, pressure, and disturbance across the shallow shelves. Where earlier communities were shaped largely by slow shifts in posture and contact with sediment, the Cambrian seabed now experienced more frequent and directed motion as some bodies moved with greater purpose through the water column. Among the prominent predators of the Cambrian oceans were forms equipped with large grasping appendages and well-developed eyes, allowing them to locate and seize other organisms in the water around them. In the clear, sunlit Cambrian shelves, vision extended the physical reach of these animals beyond immediate contact with the substrate. Bodies that once encountered one another only when resting on the same patch of sediment could now be detected at a distance, and the space between organisms became an active arena of interaction rather than a passive gap. The water column itself became part of the physical environment of encounter, shaped by directed movement rather than by slow drift alone. As predators moved through the Cambrian seas, their bodies displaced water, creating wakes and subtle pressure changes that spread outward from their path. Small organisms resting against the seabed experienced these disturbances as passing pulses of flow, lifting fine particles into suspension and briefly altering the distribution of sediment across the surface. The trace of a predator's movement extended beyond the immediate line of travel, shaping the microenvironment encountered by other forms in its vicinity. The water around moving bodies became a medium of influence, carrying signals of motion through changes in pressure and flow. The presence of predators altered how other Cambrian organisms positioned themselves within the environment. Bodies resting on the seabed were more likely to maintain contact with sediment, reducing their profile against the water column, where they might be more easily detected. Others occupied shallow depressions or slight rises in the substrate, using the uneven texture of the seabed to break up their outlines against the background of sediment. These subtle adjustments in posture and placement changed the physical patterns of contact across the Cambrian seabed, redistributing where impressions were left and how sediment was disturbed. Predatory encounters also changed how bodies interacted when they came into contact. The grasping appendages of Cambrian predators closed around prey with defined mechanical action, applying pressure to specific regions of the prey's body. This concentrated force differed from the diffuse contact experienced when two soft-bodied forms pressed gently against one another. The mechanical interaction between predator and prey altered the immediate physical environment, as struggling bodies displaced sediment and stirred fine particles into the water column. These disturbances contributed to the dynamic texture of the Cambrian seabed, as patches of sediment were repeatedly reworked by moments of rapid movement. The development of more capable eyes during the Cambrian period further changed the physical structure of interactions within the seas. Visual detection allowed predators to orient their movement toward distant forms, creating directed paths of motion across the water column. This introduced lines of movement that cut across the gentle, multi-directional flows of currents, adding new patterns of disturbance to the physical environment. The water around these moving bodies experienced localized acceleration and deceleration, shaping how suspended particles were redistributed during each pursuit. As predation became a more prominent feature of Cambrian ecosystems, the physical layout of bodies on the seabed shifted. Organisms that could maintain lower profiles against the sediment reduced their exposure to moving water above, while others that occupied slightly elevated positions encountered greater flow and thus greater risk of detection. This spatial differentiation created vertical structure within the nearshore Cambrian waters, with distinct physical layers of interaction between the sediment surface and the water above. The boundary between these layers became an active zone of movement and encounter, reshaping how bodies were distributed in three-dimensional space. The increased pace of movement associated with predation also altered how sediment settled across the Cambrian shelves. Rapid motions lifted fine particles into suspension, delaying their deposition and redistributing them across nearby surfaces. Over time, repeated disturbances by moving predators contributed to a more frequently reworked seabed, where layers of fine sediment were mixed and resettled. This physical reworking influenced the texture of the substrate encountered by resting organisms, creating a more heterogeneous surface shaped by the cumulative effects of directed motion. Within this evolving physical landscape, the Cambrian seas supported a growing network of interactions defined by movement, detection, and mechanical contact. Predators introduced new patterns of flow and disturbance, and prey responded by adjusting posture, position, and contact with the sediment. The environment of the Cambrian shelves thus became more dynamic, shaped by bodies moving through space rather than only by the slow processes of sedimentation and current flow. The interplay between directed motion and the yielding surface of the seabed added a new dimension to the dialogue between life and environment in the Cambrian world. In the Cambrian seas, some of the best-known predators belong to a broader group of radiodonts, animals with large frontal appendages adapted for grasping and manipulating prey. Their movement through the water column altered the near-bottom flow as they passed over the seabed, and their pursuit behavior created short bursts of acceleration that contrasted with the slow drift of currents. A grasping appendage closing around a target is a mechanical event that concentrates force, and the struggle that follows can churn sediment, lifting fine particles into suspension and briefly clouding the water near the substrate. This local clouding changes visibility and alters how light reaches the seabed, a short-lived physical shift produced by the act of feeding itself. Predation also encouraged defensive behaviors that would later become more visible through hard parts, but even before that, it could shape posture and timing. Remaining still against the seabed reduces the flow disturbances an animal creates, and in a quiet Cambrian environment, the absence of motion is itself a physical strategy. When predators are present, the water column becomes a space of risk, and the safest place can be the thin, near-seabed flow layer, close to the sediment, where motion is slower and outlines are less distinct. In this way, predation reshaped the vertical structure of Cambrian habitats, drawing many forms closer to the substrate and increasing the density of activity on the seabed. In the early Cambrian seas, the range of body forms expanded into shapes that would later appear unfamiliar when viewed from the present. Along the fine-grained mud of the Cambrian seabed, and within the clear, shallow water above it, bodies emerged that combined features in ways not seen before or since. Some carried arrays of spines along their upper surfaces, projecting rigid points into the surrounding water, while others bore elongated extensions that reached forward from the head region. These structures changed how bodies met the flow of currents, altering the patterns of pressure and movement around them as they rested or moved through the water. The setting of the Cambrian shelves provided a broad testing ground for these experimental arrangements of tissue. Fine sediment continued to settle across the seabed, forming a pliable surface that responded to contact. When an organism with projecting spines pressed against this substrate, the points of contact were concentrated into narrower regions, creating punctuated impressions rather than broad smudges. Water flowed differently around these protrusions, creating small zones of altered pressure that shaped how suspended particles moved in the immediate vicinity of the body. The seabed and water column together acted as a continuous medium in which the physical consequences of each new body design were expressed. Some Cambrian forms bore elongated, flexible structures at the front of the body, extending into the surrounding water. These appendages interacted with currents before the main body did, encountering flow and suspended particles at a distance. As water moved past these forward extensions, it changed direction slightly, creating subtle turbulence that spread back toward the body. The presence of such protruding structures altered the microenvironment around the organism, shaping how water and particles were guided along its surface. This reconfiguration of flow affected how nutrients and oxygen were delivered to tissues along the body, influencing how long particular postures could be maintained. Other experimental Cambrian forms carried multiple visual structures arranged across the front of the body. These visual surfaces were oriented to receive light from different angles within the shallow, sunlit waters of the Cambrian shelves. The arrangement of these sensory surfaces altered how the body was oriented in space as the distribution of incoming light varied with posture and movement. Bodies bearing such features tended to adopt positions that maximized exposure to incoming light from above and the sides, subtly shaping how they rested against or lifted away from the seabed. The orientation of these forms in the water column was influenced by the placement of their sensory structures, tying posture to the directionality of light and flow. The early Cambrian seas also hosted forms with body plans that lacked clear counterparts in later periods. Some bodies were composed of soft, segmented elements without the firm articulation seen in trilobites, while others combined rigid projections with flexible trunks. These arrangements produced varied patterns of contact with the sediment. A body bearing both soft and firm regions pressed into the seabed unevenly, with firmer areas creating deeper impressions and softer regions conforming more closely to the surrounding contours. The resulting pattern of disturbance on the substrate reflected the internal heterogeneity of the body above it, creating a textured record of contact shaped by mixed structural properties. The persistence of these experimental forms depended on how well their physical arrangements matched the conditions of the Cambrian environment. Bodies that disrupted flow too strongly could experience increased drag, making it more difficult to maintain position against slow-moving currents. Others that failed to maintain sufficient contact with the seabed could be displaced more easily by passing water. The interplay between body shape, flow, and substrate contact acted as a continuous filter, shaping which experimental designs could remain stable within particular microhabitats of the Cambrian shelves. Over time, some arrangements proved less compatible with the physical conditions of the shallow seas and disappeared from the record. The disappearance of many of these experimental body plans reflects the selective pressure imposed by the physical environment. The Cambrian seas offered a wide range of possible configurations of posture, flow interaction, and substrate contact, but not all combinations were equally sustainable. Bodies that could distribute pressure effectively across soft seabed mud, maintain stability against moving water, and position sensory surfaces within favorable zones of light and flow were more likely to persist. Those that could not maintain such balances were gradually replaced by forms better suited to the prevailing physical conditions. Despite the eventual disappearance of many experimental designs, their presence in the Cambrian record marks a period of wide-ranging exploration of possible body architectures. The seabed and water column functioned as a continuous testing surface, expressing the physical consequences of each new arrangement of tissue and structure. Each form left its own pattern of disturbance in sediment and flow, contributing to the evolving texture of the Cambrian environment. The early Cambrian seas thus became a mosaic of shapes interacting with water and ground in diverse ways, some of which would leave lasting lineages, while others would fade as the physical dialogue between life and environment continued to evolve. Some of the most distinctive Cambrian forms combine textures and body coverings that suggest intermediate strategies between softness and armor. Certain organisms carried overlapping scale-like elements across their backs, creating flexible coverings that could bend with the body while still presenting a more resistant surface to contact. Others bore long spines that projected into the water, increasing the apparent size of the body and changing how predators approached. A spine is a simple structure, but its physical effect is large. It changes the distance at which a grasping appendage can safely close, and it changes how the body interacts with currents, sometimes stabilizing posture by increasing drag in a controlled way. The Cambrian record also shows that many experimental designs were pruned not only by ecological competition, but by the limits of development and mechanics. A body plan that works at small size may become unstable as it grows, because the forces of water scale differently with surface area and mass. A form that can maintain posture, while small, may begin to twist or collapse under its own weight as it enlarges, especially in yielding sediment. These physical constraints would have been present in the Cambrian seas as constant background filters, making some arrangements viable only within narrow ranges of size, posture, or habitat. The experimental phase of the Cambrian therefore includes designs that may have worked briefly in specific conditions before being replaced by more mechanically robust arrangements. In the Cambrian period, most bodies that moved across the shallow seas left only fleeting traces in fine-grained mud, and the majority of their forms were lost as tissues decayed and surfaces were reworked by currents. Yet in a few rare settings, conditions aligned in ways that allowed delicate structures to be preserved with unusual clarity. Along certain slopes and basins within the Cambrian seas, fine particles settled rapidly from the water column, forming dense blankets of mud that could smother resting organisms before currents or scavengers disturbed them. In these moments, the soft outlines of bodies were sealed beneath layers of sediment, capturing details that would otherwise have vanished. The circumstances that produced such preservation were highly specific. In portions of the Cambrian oceans where steep underwater slopes fed into deeper basins, gravity-driven flows of fine sediment could sweep downslope and spread out across the basin floor. When these flows slowed, clouds of suspended particles settled en masse, creating sudden deposits that pressed gently but firmly over the bodies resting below. The weight of this fine sediment conformed closely to the shapes of soft tissues, preserving outlines of limbs, feeding structures, and internal features before decay could erase them. The result was a record of Cambrian life that retained details rarely preserved elsewhere in the rock record. Within these exceptional Cambrian settings, the water above the seabed often became temporarily depleted of oxygen following rapid burial events. As fine sediment settled, it restricted the circulation of water around the buried bodies, limiting the activity of microbes that would normally break down soft tissues. This brief suppression of decay allowed delicate features to remain intact long enough to be compressed into the surrounding sediment. The sealing of bodies beneath fine-grained layers thus combined mechanical protection with chemical conditions that slowed the loss of structural detail. The Cambrian seas that produced such deposits were not fundamentally different in their surface appearance from other shallow marine environments. Sunlight still warmed the upper layers, and currents continued to move across the shelves. The difference lay in the geometry of the seabed and the dynamics of sediment transport. Where slopes descended into deeper basins, the potential for sudden sediment flows increased. These flows carried vast numbers of fine particles that could blanket the basin floor in a single event, creating a physical snapshot of the community present at that moment. The preservation of entire assemblages in such settings reflects a convergence of seabed shape, sediment supply, and water movement unique to certain parts of the Cambrian oceans. The clarity of these preserved Cambrian forms transformed how early marine life is understood. Soft-bodied organisms that left no durable traces elsewhere could be seen in detail within these deposits, revealing structures such as feeding appendages, sensory organs, and internal tissues. The arrangement of these features within the sediment allowed their relationships to one another to be inferred, providing insight into how early Cambrian bodies were organized. The rock record in these settings thus retained a level of anatomical information that would otherwise have been erased by the ordinary processes of decay and sediment reworking. Within the broader Cambrian environment, such preservation events were rare interruptions in a landscape of continual motion. Most of the seabed experienced slow deposition and frequent reworking by currents, which blurred and erased fine detail. The exceptional deposits formed where fine-grained sediment could accumulate rapidly and remain undisturbed long enough for layers to compress and harden. Over time, these layers were buried beneath additional sediment, sealing the preserved forms within rock. The resulting fossil-bearing strata represent isolated windows into the living communities of the Cambrian seas, set within a broader record that is otherwise dominated by more durable traces. The process of preservation in these settings also influenced which forms were captured. Bodies that lay directly on the seabed at the moment of burial were more likely to be preserved in full outline, while those suspended slightly above the surface could be partially displaced by settling sediment before being sealed. The angle at which sediment flows approached the basin floor shaped how bodies were covered, sometimes tilting or compressing them in particular orientations. These physical interactions left subtle distortions in the preserved forms, recording not only the anatomy of Cambrian organisms, but also the dynamics of the sedimentary events that buried them. The existence of these preserved assemblages highlights the contrast between the ordinary physical processes shaping the Cambrian seabed and the rare circumstances that allowed soft-bodied life to be recorded in stone. Most Cambrian environments continued to favor the preservation of firmer structures and durable impressions, while soft tissues were lost. In a few locations, however, the combination of rapid burial, fine sediment, and restricted oxygen created a setting in which the fleeting details of Cambrian bodies could be retained. These rare records extend the physical memory of the Cambrian seas, preserving moments of interaction between life and environment that would otherwise have passed without trace. Some of the most famous windows into soft-bodied Cambrian life come from deposits where exceptionally fine mud captured organisms as flattened films, preserving outlines and delicate structures. In such sites, organic material can be compressed into thin carbonaceous layers that trace the shapes of limbs, gills, and soft body margins. In other cases, minerals can replicate tissues soon after burial, preserving three-dimensional details in a way that ordinary muds do not. These different modes of preservation reflect variations in local chemistry, sediment grain size, and the timing of burial relative to decay. A sudden mud flow that blankets a community is sometimes described as an ablution event, a burial that arrives quickly enough to overwhelm normal scavenging and disturbance. In the Cambrian, such events could occur along the margins of shelves where fine sediment accumulated on slopes and then slumped downslope in a dense moving cloud. When the flow settled, it created a sheet of fine material that sealed the seabed surface like a lid, limiting circulation of oxygenated water and slowing decay. Over time, the layers above compressed the deposit, turning the mud to shale while retaining an anatomical record of organisms that would otherwise have left almost nothing behind. These windows do not represent the everyday Cambrian seabed, but they preserve rare moments with extraordinary fidelity, allowing the diversity of soft-bodied forms to be seen alongside the more durable traces found elsewhere. In the Cambrian seas, the surface of the seabed did not remain a passive stage beneath drifting forms. As more organisms began to move across and into the soft seabed mud, the ground itself became an active participant in the shaping of the environment. The uppermost layers of mud, once smoothed mainly by currents and the quiet settling of particles, were increasingly disturbed by living forms that pressed, lifted, and shifted the surface with repeated contact. Each movement altered the texture of the seabed, creating small ridges, shallow depressions, and faint trails that changed how water flowed close to the ground. Across broad Cambrian shelves, fine sediment continued to rain down through the water column, forming a soft layer that could be easily reshaped. When a body settled onto this surface, its weight displaced water trapped between grains, causing the mud to yield and conform to the outline above it. As the body lifted again, the displaced grains slumped back, partially filling the impression but rarely restoring the surface to its previous smoothness. Over time, repeated contact from many forms transformed large areas of the seabed into a gently textured landscape. The surface was no longer a uniform plane, but a mosaic of subtle relief shaped by biological contact. Some Cambrian organisms began to interact with the fine sediment more directly by moving through it rather than only across it. Shallow probing of the mud, slight penetration beneath the surface, and brief burial within the upper layers changed the physical properties of the substrate. Where fine sediment was disturbed, the fine grains were loosened and mixed with water, increasing the porosity of the upper layer. This mixing allowed oxygenated water to penetrate slightly deeper into the fine sediment than in undisturbed areas, altering the chemical environment experienced by organisms resting at the boundary between water and mud. The seabed thus became chemically patchy, with small zones of greater oxygen availability forming where movement was more frequent. This early mixing of fine sediment marked the beginning of a broader transformation in how the Cambrian seabed functioned. In places where movement was rare, the fine sediment surface remained capped by microbial films that bound grains together into cohesive sheets. These films stabilized the surface and limited the penetration of water into the fine sediment below. Where organisms disturbed the surface repeatedly, these films were broken, exposing fresh, fine sediment to moving water. The contrast between film-covered patches and disturbed patches created a varied seabed in which physical and chemical conditions differed across short distances. Bodies settling in these different patches encountered distinct environments, even within the same shallow bay or shelf. As the surface was reworked, the pathways of near-bottom currents also changed. Water flowing across a smooth microbial mat behaves differently from water moving over a roughened surface of ridges and depressions. The textured seabed disrupted the seabed-adjacent flow layer of water close to the ground, creating small eddies that slowed flow in some pockets and accelerated it in others. These microcurrents influenced where fine particles settled and where they were more likely to be lifted back into suspension. Over time, the redistribution of fine sediment reinforced the textured pattern created by biological disturbance, making some areas more prone to accumulation and others more prone to erosion. The physical reworking of the seabed also altered how nutrients were exchanged between fine sediment and water. In undisturbed fine sediment, organic material decays within the upper layers, and the products of that decay diffuse slowly into the surrounding water. Where fine sediment was mixed by movement, this exchange became more dynamic. Fresh fine sediment was brought into contact with oxygenated water, while organic material was redistributed, changing the local availability of nutrients. Bodies resting on these mixed patches experienced a slightly different chemical environment than those on undisturbed surfaces, influencing how long they could remain settled and how actively they could feed. These processes unfolded gradually across the Cambrian shelves, producing a seabed that was increasingly shaped by life itself. The ground beneath the water was no longer simply a receiving surface for fine sediment, but a medium continually modified by the movements of organisms. Each contact left a small physical trace, and the accumulation of countless such traces transformed the texture and chemistry of the environment. The seabed became a living surface, its properties influenced by the very forms that depended on it for support. The beginnings of fine sediment mixing also had long-term consequences for preservation. Where the upper layers were frequently disturbed, impressions left by resting forms were more likely to be erased before they could be buried by new fine sediment. In contrast, in areas of relative stability, impressions could persist long enough to be sealed beneath settling layers, entering the fossil record. This uneven pattern of disturbance and preservation means that the Cambrian rock record reflects not only the presence of organisms, but also the degree to which the seabed was being reworked at any given location. The texture of the seabed thus shaped what would later be remembered in stone. The gradual transformation of the Cambrian seabed represents a shift in the relationship between life and environment. Bodies no longer simply adapted to a static surface shaped by physical forces alone. Through repeated movement and contact, organisms began to reshape that surface, altering the flow of water, the penetration of oxygen, and the distribution of nutrients within the upper layers of fine sediment. The environment became increasingly responsive to biological activity, and the patterns of contact between body and ground grew more complex. Within the Cambrian shelf waters, this feedback between movement and substrate created a dynamic landscape. Each new disturbance altered the conditions encountered by the next body to pass over the same patch of ground. The seabed thus recorded a living history of interaction, a constantly revised surface shaped by countless small acts of contact. As the Cambrian period progressed, this living surface would continue to change, laying the groundwork for later transformations in how life and fine sediment interacted beneath the moving waters of the ancient oceans. In the Cambrian seas, the growing complexity of life was also reflected in how organisms perceived and responded to their surroundings. As forms became more active and interactions within the water column increased, the ability to detect changes in light, movement, and pressure took on greater importance. The shallow Cambrian oceans were filled with shifting patterns of illumination as sunlight filtered through moving water, creating bands of brightness and shadow that drifted across the seabed. These patterns changed with the angle of the sun, the movement of surface waves, and the presence of suspended particles stirred up by currents or by passing forms. For organisms living on or just above the seabed, light was not a constant backdrop, but a moving feature of the environment. As ripples on the surface focused and scattered sunlight, patches of brightness slid slowly across the fine sediment. A body resting in one of these patches experienced a different visual field than one settled in shade. The ability to register such differences allowed some Cambrian organisms to orient themselves within the shallow seas, aligning their forms with the direction of incoming light or adjusting posture as brightness shifted. These small adjustments influenced how forms met moving water, subtly altering the pattern of flow around them and changing how suspended particles and dissolved oxygen were delivered to their surfaces. In the early Cambrian, visual structures varied in complexity. Some forms possessed simple light-sensitive regions capable of detecting general changes in brightness, while others developed more defined eyes with multiple facets that sampled light from different angles. In clear, shallow water, these structures allowed organisms to sense motion at a distance, extending their awareness beyond the immediate boundary of contact with fine sediment. A moving shadow cast by another body passing overhead could be registered before physical contact occurred, giving the resting organism time to adjust posture or shift slightly along the substrate. The physical environment of the Cambrian seas thus began to include zones of visual awareness, where light and shadow acted as signals of nearby movement. Beyond light, the movement of water itself carried information. Pressure changes and subtle shifts in flow spread outward from moving forms, creating faint disturbances that traveled through the surrounding water. Organisms equipped with sensory surfaces responsive to these changes could detect approaching motion without direct contact. In the quiet background of mild near-bottom flow, the wake of a passing form stood out as a transient alteration in the pattern of flow. The ability to sense such changes altered how forms positioned themselves within the water column and along the seabed. A body that could detect oncoming flow might turn slightly to reduce drag, or lower itself closer to the fine sediment to minimize exposure. The development of these sensory responses changed the texture of interactions within the Cambrian environment. Bodies no longer encountered one another only by chance contact on the same patch of fine sediment. Instead, encounters could be anticipated and, in small ways, avoided or approached deliberately. This anticipation influenced how organisms spaced themselves across the seabed. Areas of high activity, where many forms moved in disturbed water, became zones of frequent sensory stimulation. Quieter patches, with fewer disturbances, offered more stable conditions for resting. The distribution of forms across the Cambrian shelves thus reflected not only physical constraints, such as current strength and fine sediment texture, but also the sensory landscape shaped by light and flow. The presence of sensory structures also fed back into the physical environment. Bodies that responded to approaching movement by shifting posture changed how they interacted with fine sediment. A slight lift of the front of the body altered the pattern of contact with the ground, redistributing pressure and modifying the texture of the impression left behind. A small turn to face or turn away from moving water changed how currents were deflected around the body, creating new microcurrents that influenced where fine particles settled. Through these responses, sensory perception became a driver of physical change at the boundary between body and environment. As the Cambrian seas grew more populated and interactions became more frequent, the sensory dimension of the environment became increasingly important. Light patterns, flow disturbances, and pressure changes formed a shifting field of information through which forms navigated. The seabed and water column were no longer experienced as static backgrounds, but as spaces filled with transient signals of movement and presence. This growing sensory richness did not replace the physical constraints of water and fine sediment, but it layered an additional dimension onto the Cambrian world, shaping how organisms moved, settled, and responded to one another within the shallow, sunlit seas. In the Cambrian seas, the growing variety of ways in which organisms moved and perceived their surroundings began to shape the structure of communities across the shallow shelves. Bodies no longer occupied the seabed in isolation, but formed loose groupings that reflected shared responses to the same physical conditions. Where currents were gentle and fine sediment remained soft, forms that rested directly on the substrate tended to cluster in patches of stable ground. In areas where flow was stronger, forms were spaced more widely, each occupying a small zone where posture and orientation allowed the surrounding water to pass without dislodging them. These patterns of spacing emerged from countless small adjustments made by individual organisms in response to the same environmental forces. Within these Cambrian communities, the movement of one body altered the conditions encountered by others nearby. A passing form stirred fine particles into the water, briefly changing the clarity of the surrounding space. As fine sediment settled again, it could coat neighboring forms with a thin layer of silt, altering the texture of their surfaces and the immediate boundary between tissue and water. Bodies resting close together experienced more frequent disturbances of this kind, while those spaced farther apart encountered longer periods of relative stillness. The physical proximity of organisms thus shaped the microenvironment of each individual, creating subtle gradients of disturbance across the seabed. Feeding strategies within these communities also influenced how forms were arranged in space. Some Cambrian forms drew nourishment from particles suspended in moving water, positioning themselves where currents delivered a steady flow of material across their surfaces. Others relied on contact with the fine sediment, extracting nutrients from microbial films or organic matter embedded in the mud. These different strategies favored different positions within the same physical setting. Along a gentle slope of the seabed, forms that filtered particles from the water tended to occupy slightly elevated positions where flow was more consistent, while those that grazed the substrate remained closer to flatter, more stable patches of fine sediment. The seabed thus became a layered surface of overlapping feeding zones, structured by the interaction between water movement and body posture. The presence of multiple feeding modes within the same Cambrian habitat altered how fine sediment and nutrients were redistributed. Bodies that filtered particles from the water removed material that would otherwise have settled to the seabed, while grazing forms disturbed the surface films that bound fine sediment together. The combined effect of these activities changed the rate at which fine particles accumulated and were reworked across the shelf. In areas of dense activity, the surface remained in near constant flux, with films broken, fine sediment mixed, and water flow disrupted by frequent contact. In quieter zones, the surface retained a smoother character, shaped mainly by the slow deposition of particles and the gentle movement of currents. The physical structure of Cambrian communities was also influenced by the early stages of reef-like frameworks formed by certain organisms. In some shallow settings, clusters of forms with firmer outer coverings created low, irregular buildups on the seabed. These structures altered local flow patterns by diverting currents around their edges and creating small zones of reduced flow in their lee. Fine sediment tended to settle in these sheltered pockets, forming softer patches adjacent to the firmer framework. Bodies settling in these zones encountered a different balance of flow and fine sediment stability than those on open flats, adding further variety to the physical conditions within a single habitat. Over time, the cumulative presence of these small buildups changed the topography of the seabed on a local scale. The surface became a patchwork of low rises and shallow depressions, each associated with slightly different patterns of water movement and fine sediment deposition. Organisms responded to these variations by selecting positions that matched their own physical tolerances. Forms that required steady flow clustered near the edges of buildups, while those that favored calmer conditions settled into the sheltered pockets behind them. The seabed thus became a landscape shaped jointly by biological construction and physical forces, with community structure emerging from the interplay between body form, feeding mode, and the movement of water and fine sediment. The Cambrian shelves supported these early community patterns across wide regions, as similar physical processes operated in shallow seas on different parts of the planet. Although the exact species present varied from place to place, the underlying structure of communities reflected the same constraints imposed by water movement, fine sediment texture, and nutrient availability. Bodies arranged themselves in response to the same basic forces, creating comparable patterns of spacing and layering across distant Cambrian habitats. The repetition of these patterns suggests that the physical logic of community organization was already well established in the Cambrian world. As the Cambrian period progressed, the growing complexity of these communities further altered the physical environment they inhabited. The seabed became increasingly textured by the combined effects of movement, feeding, and construction. Each body both responded to and reshaped the conditions around it, contributing to a dynamic equilibrium between life and environment. The sunlit Cambrian shelves thus supported communities that were not merely collections of organisms sharing space, but integrated systems in which physical processes and biological activity were tightly intertwined. In the Cambrian seas, the passage of time unfolded not as a series of sudden breaks, but as slow, layered rhythms of change written into water, fine sediment, and living tissue. Day after day, the shallow shelves received fine grains drifting down through the water column, each settling quietly onto the soft surface below. With each new layer, the seabed thickened by a fraction, and the pressure on the layers beneath increased. Over long spans, these quiet additions compressed earlier fine sediments, slowly transforming soft mud into firmer ground. Life on the Cambrian seabed unfolded within this steady accumulation, adjusting posture and position as the surface beneath it subtly changed. Seasonal cycles also shaped the character of these shallow seas. Changes in wind patterns altered the strength and direction of surface currents, which in turn affected how oxygenated water mixed downward toward the seabed. During periods of stronger mixing, the upper layers of fine sediment were bathed in fresher, oxygen-rich water, allowing organisms resting against the ground to maintain activity for longer periods without shifting position. During calmer intervals, circulation weakened and oxygen renewal near the fine sediment surface slowed. Bodies then experienced a more constrained chemical environment, prompting small adjustments in posture or position as they sought slightly fresher flow. These slow oscillations in mixing and stillness became part of the background rhythm of Cambrian life. Storm events added another layer of temporal variation to the environment. When surface conditions intensified, waves reached deeper into the shallow shelves, stirring fine sediment that had previously lain undisturbed. Fine particles were lifted into suspension and carried across the seabed, briefly clouding the water and redistributing material across broad areas. For organisms resting on the substrate, these events altered both the physical and sensory environment. The pressure of moving water increased, fine sediment settled onto exposed surfaces, and the patterns of light reaching the seabed shifted as suspended particles scattered incoming sunlight. In the aftermath of such disturbances, new layers of fine sediment smoothed over older textures, partially erasing earlier traces of contact and creating a renewed surface upon which forms settled again. The long-term accumulation of fine sediment also influenced how communities were structured across time. As layers built up, the height of the seabed relative to the water surface changed slowly. Slight rises could bring some areas into shallower, more strongly mixed zones, while neighboring areas remained in slightly deeper, calmer conditions. Over thousands of years, these subtle shifts altered the physical context of habitats, changing the balance between flow strength, light availability, and fine sediment stability. Organisms adapted to particular combinations of these factors found their preferred conditions migrating gradually across the shelf, leading to slow changes in the distribution of forms across space. Within this layered temporal framework, the forms of Cambrian organisms also recorded time in their own structures. Growth proceeded incrementally, with tissues laid down over long spans, and in some cases, rigid coverings replaced through repeated molting. Each molt left behind a physical trace that could be buried and preserved, marking a moment in the life of the organism and contributing to the accumulating record within the fine sediment. The seabed thus became a repository not only of environmental change, but of biological history, with layers of fine sediment capturing successive stages of growth and replacement. The gradual transformation of fine sediment into firmer ground over time altered how forms interacted with the seabed. In newly deposited mud, impressions were deep and easily reshaped, while in older, compacted layers, the surface resisted deformation more strongly. Bodies settling onto these firmer surfaces left shallower impressions, and movement across them produced different patterns of disturbance. The changing mechanical properties of the substrate thus influenced how organisms distributed their weight and adjusted posture. A body that spread broadly on soft mud might adopt a slightly more elevated posture on firmer ground, lifting parts of itself to reduce contact and maintain stable interaction with the surface. Over long intervals, the chemistry of fine sediment also evolved as organic material decayed and minerals precipitated within pore spaces. The products of decay diffused slowly upward, altering the chemical environment at the boundary between fine sediment and water. Organisms resting at this boundary experience these changes as subtle shifts in the quality of the water surrounding their tissues. Areas of the seabed where organic material accumulated more rapidly developed different chemical profiles than areas swept more clean by currents. The patchwork of chemical conditions across the Cambrian shelves thus changed over time, creating a dynamic mosaic of microhabitats shaped by both biological activity and the slow processes of fine sedimentation. The passage of time also reshaped the physical record of interaction between forms and fine sediment. Traces left on the surface were buried by new layers, compressed, and eventually transformed into stone. Over long spans, the cumulative weight of overlying fine sediment hardened earlier layers, locking in the patterns of contact that had once been fleeting impressions. The rock record of the Cambrian period is therefore a layered archive of countless moments of interaction, each captured and preserved within the slow march of fine sediment accumulation. The continuity of this process creates the impression of stability in the geological record, even though the living surface was in constant motion. Within this temporal landscape, the Cambrian seas supported communities that were continuously adjusting to subtle changes in their physical surroundings. The rhythms of fine sedimentation, mixing, and disturbance created a shifting backdrop against which forms grew, moved, and interacted. The environment did not change abruptly from one state to another, but evolved through overlapping cycles that unfolded at different timescales. Daily movements of water, seasonal shifts in circulation, episodic storms, and long-term fine sediment accumulation all contributed to a complex temporal structure that shaped the lived experience of Cambrian organisms. The slow layering of time in the Cambrian seas also meant that the consequences of small changes accumulated. A slight increase in fine sediment supply, sustained over thousands of years, could raise the seabed enough to alter flow patterns across a shelf. A gradual shift in circulation could change how oxygen reached the near-bottom boundary zone near the fine sediment. Each of these changes, individually subtle, combined to reshape the physical context of life across long intervals. The Cambrian world thus evolved through the quiet accumulation of small differences, woven into the fabric of water, fine sediment, and living forms that shared the shallow seas. As the Cambrian period progressed, this layered temporal structure continued to guide the unfolding relationship between life and environment. Bodies lived within a world shaped by rhythms they could not perceive directly, yet which governed the physical conditions of their daily existence. The seabed beneath them thickened, the water above them shifted in its patterns of movement, and the chemical context of their resting surfaces evolved slowly over time. Within this gentle but persistent transformation, Cambrian life maintained its dialogue with the changing surface of the planet, responding to a world that was always becoming something slightly different from what it had been before. In the Cambrian seas, the movement of materials did not occur only in the horizontal sweep of currents across shelves, but also in a slow vertical exchange between the water above and the fine sediment below. Fine particles drifting down through the water column settled onto the seabed, while dissolved substances moved in the opposite direction, diffusing from fine sediment pore spaces back into the surrounding water. This quiet vertical circulation shaped the chemical and physical environment experienced by forms resting at the boundary between water and ground. The surface of the Cambrian seabed thus functioned as a permeable interface where water and fine sediment met and continuously exchanged matter. Within the uppermost layers of fine sediment, pore spaces between grains held thin films of water. As new fine sediment settled, these spaces were compressed, and water was slowly forced upward into the overlying water column. At the same time, oxygenated water from above seeped downward into the fine sediment, replenishing the upper pore spaces with dissolved gases. The balance between these opposing flows depended on how tightly the fine sediment was packed and how frequently the surface was disturbed. Where fine sediment remained loose and frequently reworked by movement, exchange between water and fine sediment was more efficient. Where the surface was stabilized by microbial films or left undisturbed for long periods, exchange slowed, and the chemical environment beneath the surface diverged from that of the water above. This vertical exchange influenced how organic material was processed within Cambrian fine sediments. As dead tissue and waste products settled into the upper layers, they were broken down by microbial activity. The products of this decay accumulated within pore waters and then diffused upward, altering the chemical composition of the thin near-seabed flow layer at the fine sediment surface. Bodies resting on this surface experience these chemical gradients as subtle differences in the quality of the water bathing their tissues. In areas of higher organic accumulation, decay products could build up more rapidly, creating localized zones where oxygen was depleted more quickly. In contrast, areas swept more frequently by currents or disturbed by movement maintained a fresher chemical environment at the interface. The vertical structure of the Cambrian seabed thus created a layered chemical landscape that organisms had to navigate through posture and placement. A body resting flush against the fine sediment surface experienced direct contact with pore waters diffusing upward, while a body that lifted part of itself into the water column encountered a different chemical regime. Even small changes in posture could shift an organism between these zones, altering the balance of oxygen and dissolved substances it experienced. This sensitivity to vertical position influenced how forms settled on the seabed and how long they remained in a given posture before making small adjustments. The slow seepage of water through fine sediment also shaped how minerals precipitated within pore spaces. As chemical conditions varied with depth, certain minerals formed thin coatings on fine sediment grains, gradually cementing parts of the substrate. Over time, these coatings reduced porosity in deeper layers, slowing the upward movement of pore water and further differentiating the chemical environment beneath the surface from that above. The surface layer remained relatively permeable, while the layers below became more compact and chemically distinct. Organisms interacting with the surface thus encountered a substrate whose properties changed with depth, influencing how easily impressions formed and how quickly they were erased by settling fine sediment. This vertical layering also affected the preservation of biological traces. Impressions left on the surface were most likely to be preserved if they were quickly sealed beneath new fine sediment, while the underlying layers remained soft enough to accommodate compression without collapsing the trace. If fine sediment beneath the surface had already become compacted and less permeable, the impression might be shallower and more easily eroded by passing currents before burial. The changing physical properties of the fine sediment column therefore influenced which moments of contact between body and ground were captured in the rock record. The vertical structure of the Cambrian seabed shaped not only the lived environment of organisms, but also the memory of their interactions preserved in stone. In some Cambrian settings, fine-grained fine sediment settled in repeated thin layers, creating laminae that recorded subtle changes in deposition over time. Each lamina represented a moment when particles drifted down and came to rest, forming a faint line within the accumulating fine sediment. Bodies resting on the seabed during these moments could leave impressions that became incorporated into these laminae, creating stacked records of contact at different times. The vertical stacking of such traces within the fine sediment column captured the rhythm of interaction between organisms and the seabed, preserving a layered history of movement and rest across long intervals. The vertical exchange between water and fine sediment also influenced how nutrients were recycled within Cambrian ecosystems. Organic material decaying within pore spaces released nutrients that diffused upward into the overlying water, where they could be taken up by microbial communities and other organisms. This recycling created a feedback loop between the fine sediment and the water column, with nutrients moving upward and organic matter settling downward. Bodies resting at the interface experienced this exchange directly, as the seabed-adjacent flow layer of water around them reflected the ongoing circulation of materials between the two domains. The Cambrian seabed thus functioned as both a sink and a source of nutrients, mediating the flow of materials through the shallow marine environment. Over long periods, the slow cementation of deeper fine sediment layers altered the mechanical response of the seabed. The surface remained soft and pliable, while the layers beneath became increasingly firm. This gradient influenced how deeply forms could press into the substrate, and how impressions were transmitted downward through the fine sediment column. A heavy body settling onto a surface underlain by firmer layers produced a different pattern of deformation than one resting on uniformly yielding fine sediment. The changing mechanical profile of the seabed shaped how organisms distributed their weight and adjusted posture, further entwining biological behavior with the evolving physical structure of the environment. The vertical dimension of exchange between water and fine sediment thus added depth to the Cambrian world beyond what could be seen at the surface. Beneath each resting body lay a layered column of fine sediment with its own evolving chemistry and mechanics, slowly interacting with the water above. The interface between these two domains was not a sharp boundary, but a zone of continuous exchange, where matter moved upward and downward through pore spaces and along grain surfaces. Cambrian life unfolded within this permeable boundary, shaped by processes that operated quietly in the vertical dimension as much as by the horizontal sweep of currents across the shelves. In the Cambrian seas, the distribution of life across space and depth reflected a delicate balance between stability and change. The shallow shelves extended over broad areas, yet even within these apparently uniform environments, conditions varied with distance from shore, with subtle changes in depth, fine sediment type, and the strength of currents. Close to the margins of exposed land, fine material washed in from eroding rock created softer, muddier substrates. Farther offshore, fine sediment tended to be finer and more evenly distributed, settling into smoother layers across the seabed. Bodies occupying these different zones encountered distinct physical conditions, shaping how they rested, moved, and interacted with the surface beneath them. As depth increased gradually across the shelf, the character of light reaching the seabed changed. In the shallowest waters, sunlight penetrated strongly, illuminating the sediment surface and warming the upper layers of water. Slightly farther downslope, light became more diffuse, filtered by the water column and by suspended particles stirred up by currents. Bodies resting in these zones experienced different visual environments, with brightness fading and shadow becoming more persistent. This gradient of light influenced how organisms oriented themselves and where they could most effectively detect movement in the surrounding water. The depth-related change in illumination added another layer of structure to the Cambrian seascape, shaping how forms distributed themselves across the shelf. The strength and pattern of currents also varied with distance from shore and depth, Nearshore zones were more directly influenced by wave action, with periodic pulses of stronger flow reaching the seabed during storms or high-energy conditions. These pulses reworked sediment, smoothing over small ridges and redistributing fine particles. Organisms in these areas had to maintain postures that could withstand occasional increases in flow, spreading contact across the substrate, or positioning themselves in small depressions where water movement was reduced. Farther offshore, currents were steadier and less turbulent, allowing forms to maintain more stable positions over longer periods. The gradient of flow conditions across the shelf thus structured where different forms could persist. Sediment composition also shifted across these spatial gradients. Nearshore inputs of coarser material mixed with fine muds, creating substrates with variable grain sizes. Such mixed sediments responded differently to pressure, sometimes yielding unevenly beneath resting forms. Offshore, finer-grained sediments formed more uniform surfaces that deformed smoothly under contact. Bodies settling on these different substrates left distinct patterns of impression, reflecting the mechanical properties of the ground beneath them. The physical feedback between body and substrate varied with location, contributing to spatial patterns in how traces accumulated and were preserved across the Cambrian shelves. The spatial structure of Cambrian habitats also extended vertically within the water column. Bodies that rested directly on the seabed occupied a different physical regime from those that lifted portions of themselves into moving water. Even small changes in elevation altered exposure to currents and the delivery of suspended particles. Near bottom waters moved more slowly due to friction with the sediment surface, creating a near-bottom boundary zone of reduced flow. Bodies positioned within this layer experienced gentler movement of water and a more stable chemical environment. Those extending beyond it encountered stronger flow and more rapid exchange of dissolved substances. The vertical positioning of forms thus shaped how they experienced the physical environment, adding another dimension to spatial variation. The interplay between horizontal and vertical gradients created a three-dimensional mosaic of habitats across the Cambrian seas. A body resting on the seabed near shore in shallow water experienced strong light, variable currents, and mixed sediments. The same body, if positioned farther offshore or slightly above the substrate, would encounter a different combination of light, flow, and sediment stability. The distribution of forms across this mosaic reflected countless small adjustments to these gradients, with organisms selecting positions that match their own tolerances and modes of interaction with water and ground. Over long periods, changes in sea level subtly shifted these gradients across the shelf. When sea levels rose, shallow habitats extended farther inland across continental margins, spreading the zone of sunlit, well-mixed water over new areas of sediment. When sea levels fell, these zones contracted seaward, exposing parts of the shelf to erosion and concentrating shallow marine habitats into narrower bands. These shifts did not occur abruptly within the span of a single generation, but over thousands of years they altered the spatial distribution of habitats available to Cambrian organisms. The physical context of life thus migrated slowly across the landscape of the seabed, carrying communities with it or forcing them to adjust to new conditions. The spatial organization of Cambrian life also influenced how communities interacted across distance. Areas of dense activity could act as sources of disturbance, sending pulses of reworked sediment into neighboring zones. Fine particles lifted from one area could settle in calmer regions nearby, subtly linking the physical conditions of adjacent habitats. The movement of water across the shelf connected these zones, carrying dissolved materials and suspended particles between them. Within the Cambrian seas, thus formed a continuous physical network in which local conditions were shaped not only by immediate forces, but by processes unfolding across the broader shelf. Within this interconnected environment, the spatial distribution of forms created patterns of influence that extended beyond individual patches of ground. The cumulative effects of movement, feeding, and sediment disturbance in one area altered the conditions encountered by forms settling downstream. Over time, these interactions produced a shifting mosaic of habitats across the Cambrian shelves, with zones of relative stability and zones of frequent reworking continually emerging and fading. Life in the Cambrian seas unfolded within this dynamic spatial framework, shaped by gradients of depth, light, flow, and sediment that structured where and how forms could persist. Within the Cambrian world, thus offered not a single uniform environment, but a richly textured seascape of interconnected spaces. Bodies distributed themselves across this landscape in response to subtle physical gradients, weaving biological patterns into the fabric of water and sediment. The spatial complexity of these shallow seas formed the backdrop for further changes in how life would occupy and reshape the marine environment as the Cambrian period continued to unfold. Across the Cambrian seas, the flow of energy through the environment shaped the rhythm of life as surely as the movement of water and sediment. Energy entered these shallow marine systems primarily through sunlight, which warmed the surface waters and sustained the growth of microbial communities that formed the base of local food webs. Fine particles drifting through the water column carried organic material produced near the surface down toward the seabed, where it settled and became available to organisms resting at the boundary between water and sediment. The continuous downward movement of this material created a gentle rain of energy across the Cambrian shelves, feeding communities that depended on contact with the seabed. The delivery of this organic material was not uniform. Currents concentrated particles in some areas while sweeping them away from others. In zones where water slowed, fine material accumulated more readily, forming slightly richer patches of sediment. Bodies settling in these patches encountered a greater availability of organic matter within the surface layers of mud. In faster flowing areas, particles were kept in suspension longer, reducing the amount that settled locally. Organisms in these zones depended more heavily on the direct capture of suspended material from moving water. The physical pattern of flow across the Cambrian shelves thus structured how energy was distributed across the seabed. As organic material settled into sediment, microbial communities within the upper layers broke it down, converting it into forms that could be taken up by other organisms. This microbial processing occurred within thin films coating sediment grains and within the pore waters between them. The products of this decay diffused upward into the overlying water, enriching the thin near-seabed flow layer near the seabed. Bodies resting within this layer encountered a slightly different chemical environment than those lifted into the water column, reflecting the upward movement of nutrients from the sediment. The seabed thus functioned as both a sink for energy-rich material and a source of recycled nutrients, mediating the flow of energy through Cambrian communities. The efficiency of this recycling depended on the balance between sediment stability and disturbance. In areas where the surface remained relatively undisturbed, organic material could accumulate within the upper layers, supporting sustained microbial activity. Where movement frequently mixed the sediment, organic material was redistributed and exposed more directly to oxygenated water, accelerating decay and nutrient release. These differences created a patchwork of energy availability across the Cambrian shelves, with some areas acting as persistent sources of recycled nutrients and others experiencing more rapid turnover. The flow of energy also influenced the size and spacing of forms across the seabed. Larger forms required a steadier supply of organic material or suspended particles to sustain their tissues. Such forms tended to occupy positions where currents delivered a reliable flow of material or where sediment accumulated organic matter more readily. Smaller forms, with lower absolute energy demands, could persist in a wider range of conditions, settling in quieter patches where organic input was lower. The distribution of body sizes across the Cambrian seabed thus reflected the physical patterns of energy delivery, shaped by currents and sedimentation. Within the water column, the movement of energy-rich particles created vertical gradients of availability. Near the surface, freshly produced organic material was more abundant, while deeper layers depended on the downward transport of particles. Bodies that extended parts of themselves into the water column could intercept this flow before particles reached the sediment, altering the amount available to organisms resting below. This vertical competition for suspended material added another dimension to the spatial structure of Cambrian communities, shaping how forms position themselves relative to the seabed adjacent flow layer near the seabed. The transformation of energy through these pathways created feedbacks between biological activity and physical processes. As organisms consumed organic material, they altered the concentration of particles in the water and the amount settling to the seabed. Their movement and feeding disturbed sediment, changing how organic material was buried or exposed to decay. The redistribution of particles influenced the clarity of the water, affecting how sunlight penetrated to the seabed, and thus shaping the production of new organic material by microbial communities. The flow of energy through the Cambrian seas was therefore tightly coupled to the physical processes of water movement and sediment exchange. Over longer timescales, changes in climate and circulation altered the overall balance of energy input to the Cambrian shelves. Variations in surface temperature affected the productivity of microbial communities, while shifts in circulation patterns changed how efficiently organic material was transported across the shelf. These changes did not occur abruptly within the lifespan of individual organisms, but over thousands of years they reshaped the baseline level of energy available to communities. The structure of Cambrian ecosystems evolved within this shifting energetic context, responding to slow changes in the physical drivers of production and transport. The continuous flow of energy through the Cambrian seas thus underpinned the stability and change of early marine communities. Bodies rested, moved, and interacted within an environment where organic material drifted downward, nutrients diffused upward, and currents redistributed resources across space. The physical pathways of energy flow shaped which forms could persist in particular settings, and how communities were organized across the shelves. In this way, the Cambrian world was sustained by a quiet circulation of energy woven into the movement of water and sediment, guiding the unfolding patterns of life across the shallow seas. Across the Cambrian seas, the physical boundaries between environments were not fixed lines, but gradual transitions shaped by water movement, sediment exchange, and the slow reshaping of the seabed. Along the edges of continental shelves, shallow platforms sloped gently into deeper basins, creating zones where conditions changed over short distances. Bodies living near these transitions experienced a shifting balance of light, flow, and sediment stability. The shallow shelf received strong illumination and frequent mixing, while the deeper slope lay in dimmer, calmer water where fine particles settled more steadily. The boundary between these zones formed a gradient rather than a sharp edge, and life adapted to this continuity by occupying positions along the slope that matched the tolerances of different body forms. As water moved across the shelf and descended into deeper areas, it carried suspended material downslope. Fine sediment and organic particles drifted into deeper zones, settling onto the slope and basin floor. Bodies living near the upper edge of the slope experienced occasional pulses of sediment-laden flow, especially during periods of stronger mixing or storm-driven currents. These pulses altered the texture of the substrate, briefly covering surfaces with fresh layers of fine material. Organisms resting in these zones adjusted posture in response to the changing surface, settling again as new sediment smoothed over older textures. The slope thus functioned as a dynamic interface between the more frequently reworked shelf and the more steadily accumulating deeper seabed. The gradual decrease in light with depth shaped how forms were distributed along this transition. Near the top of the slope, enough light reached the seabed to create shifting patterns of brightness and shadow across the sediment surface. Farther downslope, light became more diffuse, and the visual environment softened into uniform dimness. Organisms adapted to these conditions by adjusting orientation and position. Bodies that relied more heavily on detecting movement in light-rich environments tended to remain in shallower zones, while those less dependent on visual cues occupied deeper positions where light was weaker, but conditions were more stable. The vertical gradient of light thus structured the spatial arrangement of forms across the slope. Flow patterns also changed with depth. Near the shelf edge, currents were influenced by surface mixing and the broad sweep of water across the platform. As water descended along the slope, flow slowed and became more laminar, reducing the frequency of disturbance at the sediment surface. Bodies resting in these deeper zones experienced fewer pulses of strong flow and a more constant chemical environment at the near-bottom boundary zone. The reduced disturbance allowed fine sediment to accumulate in thicker layers, creating softer, more uniform substrates. Organisms settling here encountered a surface that deformed more smoothly under contact, shaping how impressions formed and were preserved. The slope environment also acted as a pathway for the downward transport of organic material. Particles produced near the surface drifted into deeper zones, enriching the sediment with organic content. Bodies living along the slope experienced a steady rain of material, creating conditions favorable for forms that relied on contact with the sediment for nourishment. The accumulation of organic matter within deeper sediment layers also fueled microbial activity, altering the chemical profile of pore waters and influencing the upward diffusion of nutrients into the thin, near seabed flow layer. The slope thus became a conduit for energy transfer from the shallow shelf to deeper habitats. The transitional nature of the slope environment created opportunities for organisms adapted to intermediate conditions. Bodies that could tolerate moderate flow and reduced light found niches along the slope where competition from strictly shallow water forms and deeper water specialists was reduced. These intermediate habitats supported distinct assemblages shaped by the unique combination of physical conditions present at the boundary between shelf and basin. The gradual blending of environments along the slope fostered a continuity of forms across depth, rather than a sharp division between shallow and deep communities. Over long timescales, changes in sea level shifted the position of this transitional zone across the landscape of the seabed. Rising sea levels pushed the shelf edge landward, moving the slope environment over areas that had previously been part of the shallow platform. Falling sea levels shifted the slope seaward, exposing parts of the shelf to erosion and altering the depth gradient experienced by organisms. These shifts unfolded over thousands of years, but they gradually reconfigured the spatial distribution of habitats available to Cambrian life. The physical boundary between shelf and slope thus migrated across the seabed, carrying with it the transitional environments that supported particular community structures. The slope environment also influenced the preservation of biological traces. In deeper zones where sediment accumulated steadily and disturbance was limited, impressions and remains were more likely to be buried quickly and preserved within fine-grained layers. On the upper slope and shelf edge, more frequent disturbance increased the likelihood that traces would be reworked before burial. The rock record thus captures a composite picture shaped by these differences in preservation potential, with deeper slope deposits often retaining clearer records of soft-bodied forms and surface interactions. The transitional environment left its mark not only on living communities, but also on the geological memory of the Cambrian seas. Within the Cambrian world was therefore structured by a series of gradual transitions rather than abrupt boundaries. The slope between shelf and basin exemplified this continuity, offering a corridor of changing conditions that shaped how forms distributed themselves across depth. Life in the Cambrian seas unfolded along these gradients, with organisms finding positions within a shifting landscape of light, flow, and sediment. The boundary between environments became a zone of connection rather than separation, guiding the movement of materials and the organization of communities across the ancient seabed. Across the Cambrian seas, the long-term memory of the environment was stored not only in the slow accumulation of sediment, but also in the physical patterns left behind by repeated interactions between forms and the seabed. Each resting impression, each shallow trail, and each disturbed patch of sediment contributed to a textured surface that recorded the passage of living forms across time. Although many of these traces were smoothed away by currents and buried beneath new layers of sediment, some were preserved long enough to become part of the geological record. The seabed thus functioned as a temporary archive of movement and contact, continually revised as new interactions overprinted older ones. The preservation of these traces depended on a balance between disturbance and burial. Where sediment settled rapidly and disturbance was limited, impressions left by forms could be sealed beneath thin layers of new material before currents erased them. In calmer zones of the Cambrian shelves and along parts of the slope, fine-grained sediment accumulated in gentle sheets, preserving delicate outlines of resting forms and the faint paths of movement across the surface. In more energetic areas, where currents and waves reworked the sediment frequently, traces were short-lived, smoothed away before burial could occur. The geological memory of the Cambrian seas thus reflected the uneven distribution of preservation potential across different physical settings. The types of traces preserved also reflected the diversity of interactions between forms and substrate. Some traces recorded direct contact, such as the broad impressions left by resting forms pressed into soft mud. Others recorded movement, such as shallow furrows where forms slid or crawled across the surface. Still others recorded brief probing into the sediment, where an organism tested the ground beneath it or sought material within the upper layers. Each of these interactions left a distinct physical signature that, when preserved, offered a glimpse into how forms engaged with their environment. The rock record thus captured not only the forms of Cambrian organisms, but the ways in which they moved and interacted with the seabed. Over time, the repeated disturbance of sediment by movement altered the texture of the surface, influencing which traces could be preserved. Areas that experienced frequent reworking developed a more irregular microtopography, with small ridges and depressions that changed how impressions formed. A body settling onto a roughened surface left a different pattern of contact than one resting on a smooth, newly deposited layer of mud. The evolving texture of the seabed therefore shaped the character of the traces left behind, influencing how they were recorded in sediment and ultimately preserved in stone. The compaction of sediment over long periods transformed these traces into enduring records. As layers accumulated, the weight of overlying material compressed the sediment below, flattening impressions and locking their outlines into firmer ground. The chemical processes accompanying compaction, such as the precipitation of minerals within pore spaces, further stabilized these structures, turning fleeting impressions into permanent features of the rock. The gradual transformation from soft mud to stone preserved a history of interaction that spanned countless individual moments of contact between body and ground. The distribution of preserved traces across the Cambrian record provides insight into the changing nature of seabed interaction over time. In earlier parts of the period, traces were often shallow and simple, reflecting more limited movement across and into the sediment. As the Cambrian progressed, traces became more varied and complex, indicating a broader range of interactions with the substrate. This change reflects the gradual intensification of biological activity at the seabed, as more forms moved, probed, and disturbed the sediment surface. The geological memory of the Cambrian thus records a slow deepening of the dialogue between life and the ground beneath the water. The preservation of traces also depended on the chemistry of the sediment and overlying water. In areas where oxygen was limited beneath the surface, microbial decay proceeded more slowly, allowing impressions to persist longer before being erased. In oxygen-rich settings, decay and disturbance acted more quickly, reducing the likelihood that delicate traces would survive long enough to be buried. These chemical differences added another layer of variability to the geological record, shaping which interactions were preserved and which were lost. The memory of the Cambrian seabed is therefore uneven, shaped by the interplay of physical disturbance, chemical conditions, and the timing of burial. Beyond individual traces, larger patterns of preserved interaction emerged where communities repeatedly occupied the same surfaces. In such areas, layers of sediment recorded overlapping traces from multiple generations of organisms, creating dense palimpsests of contact and movement. These layered records capture the cumulative effect of biological activity over long spans of time, revealing how the character of seabed interaction evolved as communities became more complex. Within the Cambrian rock record, thus preserves not only isolated moments, but extended sequences of interaction woven into the fabric of sedimentary layers. The long-term memory of the Cambrian environment, encoded in these preserved traces, allows later observers to reconstruct aspects of how life engaged with the physical world. The shape, depth, and distribution of impressions offer clues about the weight, posture, and movement of forms that left them. The spacing of traces across a surface suggests how organisms arranged themselves within communities. The orientation of trails, relative to sedimentary structures, reflects how forms moved in relation to currents. Each preserved trace is a fragment of a larger story about the relationship between life and the Cambrian seabed. As the Cambrian period drew on, the accumulating geological memory of these interactions laid the foundation for understanding how marine ecosystems would continue to evolve. The increasing complexity of traces mirrored the increasing complexity of life's engagement with the environment. The seabed became not only a surface on which life unfolded, but a medium that recorded the history of that unfolding. Within the layers of stone formed from Cambrian sediments, the quiet record of countless small interactions remains embedded, preserving a long and gradual story of how life learned to leave its mark upon the ground beneath the ancient seas. Across the Cambrian seas, the rhythm of change extended beyond the daily and seasonal cycles of water movement into slower, more gradual shifts that unfolded across generations. The physical environment did not remain static, even when it appeared calm. Subtle changes in circulation patterns, sediment supply, and chemical conditions accumulated over long spans of time, gradually reshaping the context in which life unfolded. Bodies living on the seabed experience these changes as small differences in flow, in the softness of the substrate, and in the quality of the water bathing their tissues. Over the course of many generations, these incremental changes altered which forms could persist in particular settings and how communities were organized across the shelves. The slow reconfiguration of circulation patterns influenced how water moved across the Cambrian seas. Changes in the arrangement of continents and the geometry of shallow shelves altered the pathways along which currents flowed. Even modest shifts in these pathways changed where sediment accumulated and where water movement was strongest. In some areas, currents became more focused, scouring the seabed and preventing the long-term accumulation of fine sediment. In others, circulation slowed, allowing thicker layers of mud to build up over time. Bodies resting in these different zones encountered distinct mechanical environments, shaping how they distributed their weight and how deeply they pressed into the substrate. The supply of sediment itself also varied gradually as erosion patterns on land changed. Although the land remained largely barren during the Cambrian, variations in climate and the exposure of rock surfaces altered how much material was delivered to the seas. Periods of increased erosion sent larger volumes of fine particles into coastal waters, thickening sediment layers on the shelves. During intervals of reduced input, sedimentation slowed, and existing layers were more likely to be reworked by currents. These changes influenced the texture of the seabed and the rate at which impressions were buried and preserved. Organisms living at the sediment-water interface experienced these shifts as changes in how quickly the surface was renewed beneath them. Chemical conditions in the Cambrian oceans also evolved slowly over time. The balance between oxygen supply and demand varied with circulation patterns and the productivity of microbial communities. In some regions, improved mixing increased the availability of oxygen near the seabed, allowing forms to remain settled for longer periods without adjusting posture. In other areas, reduced circulation led to more frequent episodes of low oxygen near the sediment surface, encouraging organisms to shift position more often or to lift parts of their forms into better oxygenated water. These gradual changes in chemical context influenced which forms were favored in different habitats, shaping the long-term composition of communities. Over extended timescales, the accumulation of these physical and chemical shifts created a moving backdrop against which Cambrian life evolved. Forms that were well suited to one set of conditions could find themselves at a disadvantage as circulation, sedimentation, or oxygen availability changed. The slow pace of these changes allowed communities to adjust incrementally, with small differences in posture, placement, and interaction accumulating across generations. Within the Cambrian seas, thus fostered a gradual filtering of forms, not through sudden upheaval, but through the persistent influence of slowly changing environmental constraints. The physical record of these long-term changes is preserved in the stratification of Cambrian sediments. Layers of differing grain size, composition, and structure reflect variations in sediment supply and energy conditions over time. Bodies interacting with these changing surfaces left traces that varied in depth and clarity, capturing the evolving mechanical properties of the seabed. The rock record thus encodes a history of environmental change, alongside the record of biological interaction, intertwining the stories of shifting currents, changing sedimentation, and evolving community structure. The gradual nature of these changes meant that the Cambrian world did not transform abruptly from one state to another. Instead, the physical environment drifted through a series of overlapping conditions, each subtly different from what came before. Bodies adapted to these shifts through small adjustments in behavior and placement, rather than through sudden wholesale reorganization. The stability of the shallow seas masked the slow movement of underlying processes that, over long spans, reshaped the conditions under which life persisted. The interplay between slow environmental change and biological response contributed to the continuity observed in Cambrian ecosystems. Communities retained a recognizable structure even as the physical context in which they existed evolved. The seabed continued to support forms resting, moving, and interacting within a familiar framework of water and sediment, while the details of that framework shifted gradually. within the Cambrian world, thus maintained a sense of continuity across time, even as the foundations of that continuity were quietly reworked by long-term processes. The legacy of these slow changes extends beyond the Cambrian period itself. The patterns of interaction between life and environment established during this time influenced how later marine ecosystems would respond to similar shifts in circulation, sedimentation, and chemistry. Within the Cambrian seas served as an early stage on which the interplay between gradual environmental change and biological adaptation was rehearsed, setting precedents for the long history of life in the oceans that would follow. Across the Cambrian seas, the long continuity of water, sediment, and living form remained the defining character of the environment. Shallow continental shelves continued to receive fine particles drifting down through the water column, forming soft layers that were reshaped by low energy flow. Near the seabed, slow-moving water traced the contours of the sediment surface, carrying dissolved gases and suspended material into the seabed-adjacent flow layer where forms rested. The physical setting that had supported the early diversification of marine life persisted in its broad outlines, even as the details of circulation, sediment texture, and chemical balance shifted gradually across long spans of time. Across these shelves, the seabed retained the layered memory of earlier interaction. Beneath the uppermost soft surface lay compressed sediments that recorded countless past contacts between forms and ground. Each new settling of sediment buried earlier textures, smoothing over older ridges and impressions while preserving their outlines within firmer layers below. The surface at any moment represented only the most recent state of a continually revised interface between water and sediment, shaped by the quiet accumulation of particles and the steady pressure of overlying layers. Water movement continued to organize the distribution of physical conditions across the Cambrian shelves. Near-bottom currents slowed within shallow depressions and strengthened where the seabed rose into low ridges. These differences in flow influenced how fine sediment settled and how oxygenated water reached the near-bottom boundary zone. Bodies resting on the seabed experienced these variations as small differences in the movement and chemistry of the water surrounding them, shaping posture and position through subtle physical constraint rather than abrupt change. The chemistry of the Cambrian seas remained governed by the balance between mixing and renewal. Oxygen entered surface waters through wind and wave action and was carried downward by circulation across the shelves. Within the upper layers of sediment, microbial activity continued to process organic material settling from above, releasing dissolved substances back into the thin near seabed flow layer. The exchange between water and sediment proceeded quietly through pore spaces, creating gradients in chemical conditions across short vertical distances. The surface of the seabed remained a zone of continuous exchange, shaped by slow diffusion and gentle mixing rather than by sudden chemical transitions. Over long spans, changes in sea level, circulation, and sediment supply continued to reshape the physical setting of the Cambrian world. Rising and falling sea levels shifted the extent of shallow habitats across continental margins. Variations in sediment delivery altered the thickness and texture of surface layers. Circulation patterns adjusted as the geometry of shelves and basins evolved. These changes unfolded slowly, maintaining the continuity of the marine environment while slowly altering the physical context in which life unfolded. The Cambrian period stands not only as an interval of biological diversification, but as a phase in the long physical history of the oceans. The shallow seas of this time provided a stable yet dynamic framework in which early marine communities interacted with water and sediment. The patterns of contact, movement, and exchange established across these shelves formed the groundwork for later marine environments, which would continue to develop within the same fundamental constraints of circulation, deposition, and chemical balance. The record of these early seas remains preserved within layered sedimentary rocks, where the compressed outlines of past surfaces retain the physical memory of the Cambrian world. Within these layers lie traces of how forms once rested on soft mud, how currents shaped the seabed-adjacent flow layer near the seabed, and how sediment accumulated through slow, continuous deposition. The Cambrian seas no longer exist as living environments, yet their physical structure endures in the stone that formed from their sediments, preserving the conditions under which complex marine life first established a lasting relationship with the ocean floor. Alongside changes in circulation, the chemistry of shallow Cambrian waters reflected a vertically layered redox structure, with oxygenated surface layers overlying zones where oxygen declined within sediment pore spaces. This stratification influenced how long soft tissues persisted at the boundary between water and mud before decay, shaping which interactions could leave a trace. Early mineralized fragments, often grouped as small shelly faunas, began to appear in these settings, providing the first durable signals of hard material interacting with soft substrates. Their scattered presence across shelves indicates that mineral availability and local water chemistry varied from place to place, affecting where early skeletal materials could form and persist. In some shallow settings, low frameworks built by archaeocyathid sponges created early reef-like structures that altered near-bottom flow and sediment capture. These low buildups diverted currents, creating sheltered pockets where fine particles settled more readily, while exposed edges experienced stronger flow and greater particle delivery. The contrast between sheltered and exposed microhabitats introduced small-scale heterogeneity in oxygen delivery and nutrient recycling, contributing to the patchwork of conditions across Cambrian shelves. Trace fossil baselines from these surfaces record the earliest sustained patterns of movement across soft ground, establishing a reference against which later intensification of sediment mixing can be compared. These early patterns of distribution across water and depth established the chemical backdrop against which later interactions with the seabed would intensify. As circulation and oxygen delivery shaped where forms could remain settled, the physical character of the sediment surface began to matter more directly. The next phase of change unfolded at the boundary between body and ground, where repeated contact with soft mud altered how the seabed itself behaved. Across these interacting surfaces, early bioturbation remained shallow and discontinuous, but even limited disturbance altered the diffusion of oxygen into pore spaces. The resulting microgradients in redox conditions influenced where surface films persisted and where fresh sediment was exposed to moving water, modulating the chemical context of contact between tissue and ground. Once contact with the substrate became a consistent feature of daily existence, small differences in surface texture and resistance began to matter. From this point, Changes in how forms presented their outer surfaces to water and sediment became increasingly consequential, shaping both movement and preservation. This set the stage for the emergence of firmer outer materials and the earliest durable expressions of skeletal structure within the Cambrian environment. Localized availability of carbonate and phosphate in nearshore waters contributed to patchy mineralization, helping explain why early firm outer materials appear unevenly in the record. Variations in alkalinity and saturation state across shelves influenced which outer coverings could precipitate and persist, linking material expression to regional water chemistry rather than to uniform global change. Here, firmer outer layers are treated as a functional change in how forms met moving water and fine-grained mud. Stiffer surfaces altered drag, pressure distribution, and the depth of impression left in mud, changing how forms interacted mechanically with the seabed. These functional effects could occur even where mineralization was thin or discontinuous, reflecting changes in tissue organization and surface properties rather than fully developed skeletal systems. Mechanical stiffening of outer surfaces influenced how forms resisted deformation under their own weight and under passing flow, allowing some forms to maintain posture in slightly stronger currents or to bridge small irregularities in the sediment surface. This mechanical change modified the microtopography of impressions and the way near-bottom currents were deflected around resting forms. Small shelly fossils are addressed separately as a preservational and material signal in the geological record. These scattered mineralized elements reflect where local water chemistry and saturation states allowed durable materials to precipitate and persist. Their uneven distribution across Cambrian shelves records regional differences in carbonate and phosphate availability and does not imply that all forms with firmer outer layers produced preservable skeletal fragments. The appearance of small shelly elements also reflects episodic conditions in which rapid burial followed shortly after deposition, reducing dissolution and breakage in high-energy settings. In calmer pockets, early mineralized fragments were more likely to be incorporated into fine laminae, linking preservation to local sedimentation rates and early diagenetic conditions. As forms diversified in how they rested and moved across soft ground, encounters within the water column became more frequent. In these denser settings, motion itself altered local flow fields and the distribution of suspended particles, increasing the likelihood of contact between moving forms. This shift in encounter rates changed how space was experienced across the shelves, setting the physical context for more directed interactions between forms. Directed movement through near-bottom flow altered wake structure, producing pressure gradients that could be detected by nearby forms. These wakes decayed over short distances, but within crowded patches, they increased the frequency of near encounters, reshaping spacing and posture across the seabed. As encounter rates increased, the physical signals carried by light, pressure, and flow became more informative within the near-bottom boundary zone. Small changes in illumination and wake structure provided early cues of nearby movement, extending awareness beyond direct contact with sediment. Light fields near the seabed were further modulated by suspended fines resettling after disturbance, softening contrast over short intervals. This transient turbidity altered the reliability of visual cues and favored sensitivity to near-field pressure, changes within the thin, near-seabed flow layer. as directed movement and active pursuit altered encounter rates within near-bottom flow, the selective pressures shaping body plans intensified. Small differences in outline, flexibility, and surface interaction translated into different responses to moving water and contact with sediment. Against this physical backdrop, a wider range of experimental forms emerged, each expressing alternative solutions to stability, drag, and posture in the nearshore Cambrian waters. Variations in stiffness along the body length altered how force was distributed during contact with the substrate, shaping the depth and geometry of impressions in fine-grained mud. These mechanical differences contributed to the uneven preservation of experimental forms across settings with different sediment consistency and flow. The diversification of form did not unfold in isolation from the ground beneath these forms. How these experimental outlines met soft seabed mud influenced both their immediate mechanical interaction with the seabed and the likelihood that contact would be recorded. This connection between form and substrate set the stage for changes in how the sediment surface itself was reworked through repeated movement and contact. Where shallow mixing was more frequent, early stages of sediment disturbance remained discontinuous, but repeated contact gradually loosened surface films and increased porosity in the uppermost layers. This incremental change in surface properties altered the residence time of impressions before burial, linking community activity to the evolving preservation window at the sediment to water interface. Thank you for listening to the Sleepy Mind channel. I hope you have enjoyed spending time learning about the Cambrian period.